Good morning, everyone. Welcome to this first parallel session. So the title is Wind and Wave Energy Systems. We are co-chairing this session with the colleague John Martinez Molina. By the way, I'm Silvio Simani. And I'm introducing the first speaker, Guglielmo Papini. The title of the presentation of the paper is Accommodating Sensor Faults in Wave Energy Optimal Control. So the stage is yours. I don't know if you prefer to use this one, especially if you are moving.
Yeah. Good morning, everyone. I'm Guglielmo Papini from Politecnico di Torino, and today I'm presenting this work regarding accommodating sensor faults in wave energy optimal control. Well, essentially, a brief introduction of wave energy. The objective of this technology is to extract energy from the wave motion, and this is done by means of devices called wave energy converters. In literature, one can find a bunch of these devices and different architecture. For instance, here it's an example of an attenuator type, which moves along the wave, the motion direction. Or we can have something like the most classical heaving point absorber. It is a technology which exploits the vertical motion of the wave and the relative motion between the power takeoff system and the wave produces energy. Then we have a concept like a flap, so we have oscillating wave energy conversion system, for instance, which, as you can see, is a very different technology, such as inertial mass wave energy converters, which exploit essentially an internal reaction-based mechanism, such as a gyroscope, a pendulum, a gyropendulum, whatever, to create a relative motion between the primary mover, which oscillates with the wave motion direction. Or we can have something really different, such as oscillating water columns, which basically exploit the air pressure inside the chamber to drive air turbine, essentially. So, as you can see, in wave energy, we have a lot of different technologies, and so a common thing to do is to recognize in the common, essentially, subsystems. So we can have, generally speaking, in a wave energy converter, a floating buoy, which moves alongside with the wave direction, a power takeoff system, which is in charge of extracting the mechanical energy and convert it into electrical one, then a mooring system, which is the subsystem which takes in place the wave energy converter, basically. So this technology is, however, still underdeveloped that they're trying to exploit the economical viability features to enhance basically the commercialization of the wave energy. In this context, energy maximizing control constitutes a fundamental component to lower the levelized cost of energy of the technology. So, energy maximizing optimal control, generally speaking, has the objective of directly maximize the power extraction while respecting physical and technological constraints on the technology. The solution of the optimal control problem in this case is pursued via standard optimal control techniques such as model predictive control. Going a bit into detail of the optimal control problem, we can find a non-standard cost function which differs significantly from the standard trajectory tracking objective. In this case, it's power maximization, so the shape of the cost function is a bit different. Then we have two other actors, let's say. The first one is the wave excitation force signal, which has to be estimated because essentially this signal can't be retrieved via measurement via physical sensor due to technological infeasibility features. The second one is the non-causality of the optimization problem, which is restored usually via autoregressive modeling the future behavior along the prediction horizon of the wave excitation force itself. So basically, strong point behind this approach is to rely on a mathematical model which has to be, on one side, computationally light, to be optimized in real time, and on the other side, must be representative of the main dynamics of the system. So, for instance, considering discrete linear dynamics of the WEC hydrodynamical behavior, the problem is transcribed directly into a QP problem, as every MPC, for instance, optimization approach does, and then optimized in real time in a receding horizon fashion. However, to solve this problem, we have to estimate both the state of the system and the wave excitation force. And here comes the bad points, essentially, because wave energy application entails a huge uncertainty on the hydrodynamics of the system, as long as an operational environment which can damage, for instance, the system, introduce other sources of uncertainty, and in combination with the previous approximations introduced by the hydrodynamics of the system, we can finish in a discrepancy, a huge discrepancy, between the original system and the contour-oriented model. If such discrepancies are not accommodated directly, the optimal contour strategy may end up in an unsatisfactory behavior from the power maximization objective, the constraint handling, and it also can entail severe consequence for the integrity of the system. In this scenario, so the optimal contour one of wave energy converters, FDI and FTG may be presented as a solution to improve reliability of wave energy, though they are not still well developed in the field of wave energy until now. So, driven by this necessity, what we have thought is to consider a critical fault for wave energy optimal control, which is the WEC sensor motion fault. Why this is a critical fault? Because essentially this sensor, the IMU, the encoder for instance, is employed for both state estimation and wave excitation force reconstruction. So this signal coming from the sensor can't be reconstructed via standard assumptions of hydrodynamic modeling, because, as I was saying, we have a lot of uncertainty and we can't just directly feed through the control input to the model and obtain a sensor reconstruction. So, in this work, we have thought that we can exploit the non-standard modeling assumption of modeling the PTO dynamics, which essentially have a way faster dynamics than the hydrodynamic one, to exploit the connection between the WEC sensor motion, the WEC motion itself, and the internal variables of the power takeoff system. So, as I was saying, the idea is to provide the state and wave excitation force estimator with a correction of the actual measurement. This correction is given by exploiting the two-dimensional modeling of the power takeoff itself, by exploiting the voltages, the driving currents, and the actual coupling between the WEC motion and this power takeoff system. So, then the original hydrodynamic state estimator, state and wave excitation force estimator, is fed via a corrected version of the sensor measurement of the wave energy converter. The wave excitation force in particular is obtained via internal model observation principle by modeling the wave excitation force per se as an harmonic oscillator. So we are essentially putting some constraints and some frequency domain behavior on the wave excitation force. On the other side, the, let's say, secondary observer provides a correction of the measurement of the wave energy converter sensor motion by using the same principle, so by modeling the velocity of connected with the power takeoff system as a random walk process, which is at the end a mild assumption. We are not putting a particular behavior behind this signal, and then reconstructing directly the fault affecting the wave energy converter sensor motion. So, essentially for numerical, let's say, validation, we have considered as a benchmark a linear hydrodynamical model of the wave energy converter. The system is tested under optimal control condition by using a model predictive control. And this is tested under irregular wave scenarios. So it means basically that we have taken a Jones swap spectrum representation from the Pantelleria site, which is in southern Italy, and we have fed the system via realistic forces exciting the system under general operation. So in this case, the velocity sensor fault is just simulated as a scaled version of the original velocity of the system, in this case 80%. And we have thought to divide, let's say, on one side, the evaluation of the energy maximization performance, and on the other side, the velocity constrained handling capabilities. So the first comparison is done using an unconstrained optimal controller, and the second one by inserting the constraints. For this comparison, we consider basically three scenarios. The first one, which is the nominal one, is just the optimal control solution in absence of faults, obviously, to constitute the benchmark for comparison. The second one is the DEM, the damaged one, so is the optimal control solution with the presence of fault and without the proposed accommodation strategy, essentially. The third one is the optimal control solution with the accommodation strategy of the observer. For the results, speaking of energy production capabilities, we can see that inserting the fault, so the DEM one, presents a way worse energy extraction behavior than the optimal control solution. This essentially is due to the fact that the wave excitation force, as you can see in the figure on the right side, is not estimated properly as long as the state of the system due to the discrepancy between the actual measurement and the actual velocity of the system. On the other side, the proposed accommodation strategy manages almost to restore optimal control conditions, essentially because it manages to estimate the fault on the sensor of the WEC. So we are reconstructing, let's say artificially, we are estimating the true velocity of the system, and we are feeding the optimal controller with the true velocity. So the optimal solution is reached another time. The same holds for the constraint satisfaction performance. So if the damaged system doesn't reaches the limits, reaches and overpasses the limits, so entailing maybe a dangerous situation for the wave energy converter, so essentially not considering the faults on sensor may cause damages, as we were saying in the introduction. The proposed accommodation strategy, as we have seen for the power production performance, restores almost optimal control conditions, also from constraint satisfaction. So essentially, summing up, we have seen that wave energy, optimal control in wave energy is a fundamental component, so we can't just get rid of it, but relies essentially reliability. It has reliability issues. FDI and FTC in this framework are capable of matching essentially such needing, though they are still undeveloped. To the best of our knowledge, until now, anyone has considered to couple FDI and FTC with optimal control condition in wave energy. So we have thought to develop a benchmark, let's say a first application for a serious sensor fault in wave energy optimal control, and we have proposed an observer-based approach to restore optimal conditions. We have seen that under the assumption of this work, the proposed technique, basically working under realistic condition, manages to restore optimal control solution for both energy production performances and constraint satisfaction one, while neglecting such fault will result in a degradation of the system performance, essentially. Thank you very much.
Thanks, Guglielmo, for your presentation. If there are some questions or comments for Guglielmo, we have time. Yes, please, Vicens. I can.
When you present the MPC, you comment that you use the linear version. I guess you linearize, no? Around a point, or?
We have considered directly linear dynamics. Okay. We didn't linearize the nonlinear model. We have just done system identification in a linear side, and we have neglected, for instance, nonlinear restoring forces.
Okay.
For the main dynamics of the system, it's essentially a mass spring damper. So.
Okay. Because for improving the control, of course, you present a manner. Have you considered using more elaborated model for the MPC?
Obviously, thanks for the question. Okay. That's the next step.
Okay.
For now, we have done the benchmark, and we have seen that just for the linear case, it works. So perfect. We will move soon to the nonlinear one.
Thank you.
Any other comment? Thank you, John.
Thank you for that nice presentation. So I would like just to understand how it works properly. In fact, I'm looking for a power curve.
Yeah.
Something like, what is the degree of freedom that we have to optimize? Because it's not really, I don't understand in fact. So what is that degree of freedom? Because normally force and velocity is imposed by the wave, and you have to be a little bit delayed with respect to that. You have just to control the speed of the generator, I don't know. So what is exactly the degree of freedom?
Good. Thank you for the question. Well, actually, here we are considering just a heaving point absorber, so the one I was speaking of in the introduction, and we are considering the vertical degree of freedom of the buoy motion. So we have the power takeoff, which is aligned with this degree of freedom, and controlling the speed of the power takeoff, in this case, means controlling directly the velocity profile of the buoy. So essentially...
Okay, is it not something like controlling the damper or the stiffness of the system?
Well, no, in this case, we are not controlling parameters, but we are directly feeding the system with the optimal control action. Because the power takeoff, in this case, is a linear permanent magnet motor, so can have also reactive peaks, reactive power peaks, and so we can provide directly the system with the control action without parameterization, which at the end is the solution of the optimal control problem applied in the preceding horizon.
Thank you.
Okay, let's thank the speaker again. Thank you. So we can move to the next presentation that will be given by Dimitri Moros, Neural Networks for Offshore Wind Turbine Converter Failure Prognosis. The stage is yours. Okay, thank you.
All right, good morning, everyone. I'm Dimitri Moros. I'm an engineering doctorate student in the ID Core program, which is a joint program between the universities of Edinburgh, Exeter and Strathclyde, and I do my research for EDF R&D in the UK. So today what I'm presenting is a bit on trying to predict offshore wind turbine power converter failures, and this is being done sort of in the context of the operator of a wind farm trying to reduce their maintenance costs. So that's something to bear in mind, that we're taking very much the operator's perspective in this case, and that brings with it some benefits and limitations, as you'll see. So just sort of what I'm covering, I'll give a bit of background, that's why we're doing this. I'll introduce this data-driven framework that we're trying to develop to reduce maintenance costs at our wind farm, but today the focus will be on sort of stage 2, which is developing failure prediction models. I'll cover a bit about what data we've got, then what model we've tried to use, how the model's performed, and then this point, which I think is quite an important point, is how does the model perform when we're taking the context of actually making a maintenance decision? And then finally, some sort of future work and developments we can take on that. So, background to the problem. Approximately 30% of lifetime costs of an offshore wind farm are related to operations and maintenance. This number goes up or down depending on where your wind farm is, but it's pretty significant. So there's opportunities in there for cost savings. Current maintenance practices at wind farms are typically either reactive, so we're waiting for something to break and then fixing, or preventative, so more sort of regular time-based replacement policies. And they're considered potentially not optimal. So if we're reacting to failures, we're getting downtimes and lost revenues, so lost production from our asset. Whereas if we're replacing on a more regular scale, we're maybe doing maintenance that we don't need to do, and therefore wasting component life and potentially money. So the ideal is to move towards more condition-based and predictive strategies. So what we're trying to develop towards this is a framework that can be applied by an operator to any asset, but in our case it's an offshore wind farm. And it's a step-by-step process to reduce your maintenance costs. So the first stage is focusing on your data analysis, so that's essentially trying to tell you what is costing us lots of money and why is that costing us a lot of money. And then that informs you, okay, what do I need to develop failure prediction models for, and what do I have the data to do that for. And then once we've got the failure prediction models, this feeds into some maintenance schedule optimization, which takes into account other constraints such as weather forecasting, vessel fleets, and then finally we've got to benchmark our methods to see are they actually any good. So today the focus is really on stage 2, which is reducing turbine downtimes by providing failure predictions and hopefully eliminating any unnecessary maintenance actions. So I mentioned power converters in the title, so why power converters? So we did a bit of data analysis, and this graph sort of shows you the impacts of different subsystems on the turbine on maintenance costs and revenue losses due to downtime. And for us, we found that the power converters, which fit in the electrical subsystem, drive the vast majority of revenue losses due to downtime, and a pretty significant portion of the maintenance costs, which is why we decided to choose power converters as the focus of our failure analysis. So what do power converters in a wind turbine actually do? Well, their purpose is to change the variable frequency electricity produced by the wind turbine to a fixed frequency required by the electrical grids. And it's essentially a set of IGBT modules put together in a back-to-back AC, DC, AC converter layout connected by a DC link. And you've got 3 units per side of the turbine, so 1 per phase, 1 on the generator side and then 1 on the grid side. So the data we've got access to comes from a 27 turbine offshore wind farm in Teesside. Turbines are 2.3 megawatts each. And we've identified within our data set, we've got 16 failures in operation of our power converters, which we refer to as corrective replacements from this point. In terms of monitoring data, we have the SCADA data, which is 10-minute average timestamps. And we have this data for essentially 4 years of operation. So the sort of tags we've identified that we have accessible to us in the SCADA data that might be relevant to predicting these failures are the ones presented in the table. So got our active power, wind speed, coolant pressure, which is the pressure of the coolant on the grid side converter, and then converter temperature, which is actually the temperature of the coolant fluid. And then tower humidity and pressure ratio is the last one, which is a feature we've engineered, which is the ratio between the pressure and the temperature. And these have all been scaled, either min-max scaling or the active power has been scaled against the rated power of our turbine, so 2.3 megawatts. Okay, so how have we set up the problem? Well, we decided it as a binary classification problem where the target variable is the time to failure. In this case, we've set 8 weeks as the boundary, so our converter is either more than 8 weeks to failure or less than 8 weeks to failure. And what we're doing is we're classifying each 10-minute data point. We have a very imbalanced problem, as I'm sure you can imagine. There's many more examples of healthy data than there are of faulty data. And so we've resampled our data to a ratio of 5 to 1. And at this point, so we've trained 16 models. And we've kept 1 replacement separate for testing. So if you remember, I said we found 16 failures in operation. What we've done is we've taken one of those as our test data, and then trained our model on the data related to the other 15. And in terms of our evaluation metrics for the model, we've decided to use precision and recall. A high precision model will give us fewer false positives, but potentially miss more of the actual failures in operation, whereas a high recall model offers the converse. We found that a corrective replacement of a converter is about 4 times as expensive as a preventative replacement, so we can afford a few sort of more false positives than we can the false negatives. So we've used a pretty simple model, especially compared to what others have presented in the conference so far, but it's just a very basic, fully connected feed-forward neural network with 2 hidden layers. So moving on to some of the results. So across the top, the numbers across the top are which failure was used as the test data. So you see there's 16 there. And the numbers highlighted in blue are the models that we think performed well enough. And as you can see, that's only 4 out of 16, which isn't a great strike rate. And you'll see that there's a lot of variability depending on which failure was used for testing. And some of the models performed with absolutely 0 performance, which obviously isn't great. So then the other thing to take into context is actually, if you're trying to make a decision on maintenance, having one prediction of whether it's healthy or not every 10 minutes isn't very useful. It'll be, quite frankly, it's confusing for maintenance teams. So what we've decided to do is we've resampled that data to a modal daily prediction. And so what you can see in the graph here is along the x-axis we have our days until the actual failure point. So 0 is the point of failure. And the y-axis is the output, the modal output of our model. And this is sort of comparing what we consider a well-performing model on the left and a very badly performing model on the right. So you can see the model on the left, pretty much from the 8-week point, or just before the 8-week point, starts to predict that our converter is unhealthy and doesn't really make any sort of false predictions from that point onwards. But if you look at the model on the right, it's a bit all over the place, and to be honest, it's basically useless, particularly if you're trying to make the maintenance decision. So that's not great. But what's more important actually is how do we make a decision related to the outputs of these models to do our maintenance? So what we've done is we've tested a few sort of decision-making scenarios. So, for example, if our model has taken 3 consecutive days where the modal output is your converter is unhealthy, we'll make a decision to replace the converter. Or 7 or 21 or sort of a weekly modal thing. We've tested 10 different scenarios, but I'm just presenting a sample here. And in the table where it says yes, that means we made the correct decision to replace the converter. So now you can see actually when you consider performance models in the context of this, it performs well for about half of the test converters, which is an improvement. It's still not great, but it's an improvement. To me that sort of highlights, actually when we're designing these models, we really need to be considering actually how they're going to be used and how people are going to make decisions based off of them. So we've still not got a great model. What might be causing the poor performance? So the first thing is it might not be a very good model. We've not taken into account any time series considerations. So obviously it's time series data, and we're just considering each data point in isolation, which is obviously a deficiency. Second is we might have insufficient data. Within wind turbine power converters, there are a lot of different failure modes which can produce different symptoms. And it might be that we don't have enough data within our training data set to capture these different failure modes. And so when we're testing them on some of the converters, they're displaying a unique failure mode that isn't present in that data set. Finally, we might actually have just not the right data. I showed you that SCADA data we have, it's actually quite limited. And we might not be monitoring the right parameters where the symptoms of the failures are showing up. And our sampling frequency might be too low. One sample every 10 minutes might not be able to pick up the way in which the failures develop for the power converters. And the last one, which I've not put on here, which is a bit pessimistic, is that some failures just might not be predictable. Some can be caused by lightning strikes or insects that get onto the power converters. if anyone's got great ideas on how you can predict that, please let me know. That would be great. So what are we going to be able to do next? Well, first thing is to try using a more sophisticated model, where we take into account some time series aspects, which many other people have presented on in this conference. And the second, which I think is probably the most important, is collecting better and more data. I think we need to understand the symptoms of various faults better and collect the data that's more directly related to these faults. And I think that will lead more towards a better performing model than if you just try and sort of shotgun approach with different models, different random data to see what works. I think you can approach this in a much more considered way and collect more relevant information. And finally, we can increase our examples of failure. So we could either try and collect data of failures from other wind farms or try and use synthetic data to generate this. So what can we actually take from what we've learned today? There's potential that deep learning methods could be promising for converter failure predictions, but based on the SCADA data that we have available as an operator, it's very hard to create reliable and generalizable models. In my opinion, the most important thing to improve the performance of our models is targeting the collection of the right sources of data. And then finally, when we're designing these models, we really need to be considering how they're actually going to be used in operation. What's the maintenance decision process, and how can we design the models such that they work well in this scenario? So these are some of the references. The papers by Katharina Fischer at the Fraunhofer Institute give a lot of detail on power converter failure modes, and the others give some other interesting insights as well. So thank you very much. I'd like to thank the EPSRC and ARC for funding this, as well as EDF. And I'd love for any questions, advice, tips, whatever you guys can offer. Thank you.
Thank you to the speakers. Demeter, thank you. If there are, we have more than 5 minutes for comments. Yes?
Thank you for that presentation. So just for curiosity, in fact, you take data from a SCADA, right? That data is available every 10 minutes, and you have average data. So probably, I don't know, you filter a lot of it. So how can we find something with that data in a converter that have working in a nanoseconds or milliseconds, right? So what is the goal? To find something, a correlation with some filtered data?
You're exactly right. And that's sort of what I was trying to get across with. I don't think we have the right information contained in the SCADA systems. So as an operator, if we're trying to develop these models, it's very difficult for us in relation to the power converters especially. So yeah, I guess the goal is we need to target collection of the right data, as you were saying. You know, in that 10 minutes, how's it going to show up?
Final question for me is the control is also a data, so you don't use that information?
Yeah, so this is, again, one of the limitations of being the operator is we don't have access to that information. It's kept by the turbine manufacturers and OEMs. Yeah. So there's this almost like divide. It's weird. We've got the information about failures in operation, but we don't necessarily have the information about the right monitoring systems. So yeah, trying to sort of bridge that gap would be useful.
Thank you.
As a question, technical one, have you identified the root cause or main reason of failures in the IGTV transistor block in the inverter?
At our wind farm, no. There's not been any sort of post-mortem assessments that I'm aware of. Those two papers by Katharina Fischer, she looks at a lot of the main failure modes. The most interesting thing you can take from that is actually what she's found is the typical failure mechanisms at a wind farm aren't related to aging of the converters. There's a lot of infant mortality systems. The main causes are either faults in the driver boards that control the systems, or I'm trying to remember what the other big ones are, but Yeah, it's related to that. But then also, as I mentioned, a non-insignificant portion is related to things like lightning strikes, insects getting onto offshore wind farms, because apparently they like the silicon, and that sort of causing sort of arc over events as well. But one of the difficulties in identifying the main failure modes is some of these failures are very destructive. So you're left with a converter that looks like that one on the top right. So it can be quite hard to identify the root cause for a lot of these.
Any other comments? Or yes, please.
Thanks for a great talk. I wonder if you consider the robustness of the neural network. So, neural network can be very sensitive to noise in the data. So, because you are using a binary classification, so I wonder whether you consider the robustness.
Yeah, that's sort of a next step to look at for sure. Because yeah, as you say, and the data we have, the operational data is very noisy. And particularly when you compare that to the work that's done in sort of academia where it's very simulation based. If you look at the graphs, you just sort of look at it and be like, wow, what's going on here? But yeah, that's definitely a next step.
Thank you.
So if there are no other comments, thanks. Let's thank the speaker again. Thank you. And now we move to the third presentation that will be given by Alessio Dalla Bona. And the title is Friction Estimation for Condition Monitoring of Wind Turbine Hydraulic Pitch System. The floor is yours.
Thank you. All right, good morning everyone. My name is Alessio Dalla Bona. I'm a PhD student in the Technical University of Denmark. And today, as introduced by Professor Simani, I will give you an introduction to this investigation that I led with my colleagues, Mons Blanc and Dimitrios Papageorgiou, related to friction estimation for condition monitoring purposes in wind turbines, and in particular in the hydraulic pitch system. So the agenda will be divided in the presentation will be divided into two main parts. I will give you a context and the motivation for the investigation, and then I will go in detail in the algorithm. This investigation is inserted into a project that we're collaborating with, which is called HiRel, so high reliability, which aims at lowering the cost of energy in wind turbines by increasing their uptime. There's a lot of university and industrial partners with us. In particular, we're responsible for the fault-tolerant control part. So we started the investigation by checking what are the mitigable, detectable, and measurable faults, and then we will try to apply some fault mitigation strategies, both in simulation. We have a high-fidelity simulator based on the very common OpenFast, and then we will also, at a later stage, test the algorithms on an experimental setup of the pitch system. So the goal of the project, as introduced by the title, is to being able to estimate friction in a specific component of the pitch system of wind turbines, which is the hydraulic cylinder. But before getting to that, I just give a quick introduction of what pitching is in a wind turbine, for those of you that are maybe not familiar. So the scope is to twist the blade on itself, such that we're able to control the amount of energy that is extracted from the wind and give it in rotation to the actual rotor. If we take a closer look to this system, at least for high-power wind turbines, which are the focus of our investigation, we can see that the pitch action is performed by an electro-hydraulic system, where we have an hydraulic cylinder which is controlled, which is driven by a directional control valve, which allows us to control the flow in each of the two chambers, that then generate an hydraulic force based on Pascal, and the cylinder contracting and extending is connected to a bearing that is actually rotating, and the blade rotates together with the bearing. So the first question that you'll probably ask yourself is, okay, why are you interested specifically in the hydraulic pitch system? Let's assume that a fault happens. The most common scenario is that one of the three blades will have some kind of failure or fault at the beginning, so there will be an imbalance. when there's an imbalance in the wind turbine, we will start having some oscillation of the tower or of the rotor as a whole, and then we are not really able to guarantee any safe operation anymore in some circumstances. So what's usually happening is that we have to shut down the turbine, with other problems of having maintenance and the missing revenue, which is what we're focusing on. It also turns out, as also was spoiled by Professor Ron Patton in the first plenary, that around 20% of the faults in the wind turbine are associated with the pitch system. So it's probably worth investigating what can we do with fault tolerant control. And then the second step is why the friction in the cylinder, specifically. It turns out that the root cause for most of the faults in the pitch system is associated with oil contamination. And you will say, okay, this is not really friction itself, but it evolves in some other phenomenon that are directly associable with an increase of friction, starting from the formation of sludge, the damage of some sealing, of some seals, in case like the oil is not lubricating anymore the components, and then this can lead to metal-metal contact and eventually leakages that are the point at which we have to shut down the turbine. So we can see that friction, assuming that we are not really able to detect problems in the oil, is actually a very good first indicator for condition monitoring. The only problem is that we are not really able to detect a change in friction, at least with standard structural methods or model-based methods. And this is clear by looking at the dynamics, the dynamical equation of the cylinder. Because why we're using this equation for proving the point is because it's the most natural equation where the friction shows up as a term. We're able to measure the pressures, we have this assumption, so we're able to estimate, to calculate actually, the hydraulic force. We may also have an indication of what the nominal friction is, but we will still have a disturbance which is associated with the wind trying to move the blade on itself, and then this is reflected into an external load being experienced by the cylinder in the dynamics. This is unknown, and if we also have a fault or increase in the friction, we don't really know whether it is like the disturbance that is actually varying in amplitude or if it's actually the friction. So the problem is now being able to separate these two signals. So we take the dynamical equation, we lump the friction as a single term, and then we will have to separate the two. What's the problem? The problem is that the friction is very small compared to the loads that we're experiencing on these kind of systems. So we can't really do anything on that sense. And also the derivative is not really helping us, because for standard sampling times from which that is delivering the sensors in the turbine, we are not really able to have large peaks of friction. So we're not really able to do anything starting from this dynamical equation. Putting a sensor is not an option, because we'll still measure the total force. So we have to find a way, another algorithm, that uses some different information. And as I showed you before, we actually have a larger system that includes also the bearing dynamics. Then we can use a new equation. We pass from the force equilibrium to the momentum equilibrium. And then it turns out that this is much more useful, because now we can measure this disturbance by using a blade load sensor seen in the direction of the pitching. At this point, in order to retrieve the friction from this new equation, we actually need to estimate the derivatives of the position, of the angular position, which are in general not available, is only available as a position. And for the purpose, we decided to go with a bit of more an advanced tool, which is a discrete time high order sliding mode differentiator, which aims at differentiating the signals. We can see that the performance is quite good in the velocity. We're probably satisfied. We're not quite satisfied in the acceleration, but that's because we're working in simulation in a high fidelity scenario. So we have noisy signals, and we cannot really crank up the gains to improve the acceleration estimation. Otherwise, we'll just measure noise. So as a first solution, if we try to use this estimation to calculate the friction, we obtain the gray solution, which is giving us an indication, but still not quite good, because we have this very high frequency component associated that we're missing some dynamics in acceleration. Good thing is that we have an indication of this high frequency motion of the cylinder, which is due to the fact that when we're pitching the blade, we have both a macro pitching action, which is what we're actually interested in, and on top of that, because of the nature of the system, we have some micro pitching high frequency oscillation, which is what we're really struggling to reconstruct. So we have the measurement, we have an idea of what these frequencies are. We just designed a band-stop filter, and we're able to retrieve now the green signal, which fairly good approximates the actual friction that we obtain in simulation. So we can assume that we have a good reconstruction of the friction. Now we have to find out a parameter that is allowing us to systematically assess that a change has occurred. For the purpose, we modeled the friction with a standard, simple, symmetric model, where we included only the Coulomb static coefficient. Since there's like a lot of operations to reach this point, on a realistic scenario, it would be difficult to go in more detail about the modeling. So we assume, also in this case, we will have to differentiate the position of the cylinder, because in general the velocity is not very present in good quality. And then we have our regressor, which is an approximation of the sine function through an hyperbolic tangent. Linearly parameterized parameter estimation problem. You know better than me what we use. We use probably recursive least square as a good solution. But we can see that there's a slight modification, because as I told you, we have a very good estimation of the angular position and the angular velocity, and the same for the linear velocity, only when we're talking about macro pitching. When the velocity is very slow, so for example the turbine is not pitching, it's staying at a constant angle, then the only thing that the differentiator is trying to reconstruct is micro pitching, and we proved that it's not very good at that. So since it's not a fault that we have to detect in a very instantaneous amount of time, we can live with freezing the adaptation when the excitation is not properly given. So in green, I stated the first solution, where we actually just use standard recursive least square with forgetting factor. And then in blue, the solution we propose when we freeze the adaptation. We can see that the tracking is much more tight. We also show that there's a large variation with the axis on the right in the viscous coefficient, which is instead used in the simulation for modeling the friction. And we can show that the algorithm is insensitive to variation in other parameters to prove some robustness, at least at simulation level. So once we tune the parameter estimator, we leverage it to see what is the potential in the capability of assessing a change. So at first, we just have some recordings. We assume to have available, to run the simulation on healthy data, so we can find a threshold by setting a maximum over the data recorded up to now, and we just try to see what is the minimum amplitude of fault that we're actually able to detect. And it turns out that we can detect faults that reflect a 15% increase of with respect to nominal friction, but we need up to around 40% to actually have the signal consistently overcoming the threshold. And this works already fairly okay, but since we don't have the need to rush in the detection, we can also see if we can improve the separation of the signal by checking the signal over a larger window and using some statistical properties. So we applied a general likelihood ratio test, assuming that we only have a change in the mean, and we proved that by setting, at least on simulation level, by setting a proper window length over which we check the estimated signal, we're able to sacrifice a bit of responsiveness of the solution, but we can detect a change down to 2%, which is probably an overkill in the sense that friction is already variable in a range, but it's just to prove the point that the algorithm can be used for some application to detect eventually some very, very minor change, can be very precise. So to conclude, we developed a framework for being able to assess a change of friction in wind turbines, and in particular in the hydraulic pitch system. Why that? Because there's a lot of faults happening in the wind turbine, and specifically in the pitch system, and they turn out to be fairly dangerous for the turbine. Why the friction? Because it turns out that it's a good indicator for assessing condition monitoring and to predict the future formation of more dangerous faults before they actually happen. So we actually leverage the full pitching dynamics, and we propose a solution where we have to install a new sensor, such that we're able to first reconstruct the friction signal, then being able to estimate a parameter associated with the increase of friction, and then finally applying GLR to be able to improve the separation between the faulty and nominal case, such that we're basically able to detect whatever kind of variation in the friction. To conclude, some future perspective of the work, for sure, since we have some industrial partners, that's the plan to test the algorithm on some real wind turbines. Not super easy in the sense that this sensor is not usually available on standard turbine, so we'll have to plan it ad hoc. We are working on that. And another natural extension of the work is trying to estimate with some different information this disturbance that we have to now measure. Because yes, it's an unknown load, but if we have the measurement of the wind, we have the angle that the pitch is actually, at which the pitch is at the moment, and we have the rotation speed of the rotor. There may exist a very complex nonlinear function that deterministically determines, sorry for the word, from the measurement the actual value of the disturbance. So we're trying to apply some learning-based methods. We're starting with some neural networks to see if we're actually able to reconstruct a signal which is good enough to actually run the algorithm in a sensorless way, let's say. That concludes my presentation. Thank you very much for your attention. Yes, there's a question there.
Thank you for your presentation. If there are some comments for the author, yes. Yes, Michael. Thanks, Michael.
Yes, have you considered that friction can be lower even if a fault occurs in the system, for example, the leakages between the chambers of a cylinder?
Not really, in the sense that the most, let's say, straightforward solution is that whatever happens in general is difficult that we will be able to improve the friction. Even if there's some leakages, it's actually probably going to get worse because we're losing fluid that contains probably lubricant. So we're still trying to, like they say, damaging the structure of the system. So the case where the friction is actually decreasing, we hope that exists, but we, at least in our assumptions, is not an option, let's say.
Okay, thanks.
I would love to.
Other comments or questions from? Yes.
Thank you for your presentation. Mine is just a curiosity, for instance.
Yep.
Have you considered to decouple, for instance, the wind effect, so the wind force and the friction force by means of their spectral characteristics? Well, for instance, the wind is blowing more or less fast, but can be approximated, I think, in general as a constant, as a, not constant, as a low frequency term. While you say the friction has a high frequency component. So
Yes.
mine is just a curiosity.
We are not using the investigation the wind in the sense that we have some simulations available and there's a very stochastic component. And we couldn't really find any use, at least think about it. And the main problem is, as I mentioned, that the signals have like, the sampling time is limiting us a little bit in what we can use on signal-based. So the only use that we're thinking about using, of course, wind and other signals is using some approximation to model a very complex function. That doesn't depend only on some, let's say, aerodynamic force or anything, but it's also depending on the structure of the blade. So it's a very complex approximation that requires some learning-based method problem.
Thank you very much.
Thank you very much for your very nice presentation. I was wondering, when you were talking about the equation for the pressure,
Yes.
and where there is the term that you would like to estimate, have you ever thought about mixing the fact that you have three blades, and maybe so for one of these three blades the friction changes, and so you can somehow detect these changes using an interpolation between the three information?
That would actually be an idea, and we just didn't explore that. So that's definitely some possibility to leverage like the redundancy, let's call it, on this of the system. We'll take a definite look into that.
Okay. Okay, thank you.
Thank you.
That information, right?
Yes.
Thank you. Any other question? Comments? You have enough time to a final question or waiting a minute. So okay. This.
Thank you for the nice presentation. My question is here that you are dealing with some differential equations that inherently are nonlinear. Do you have any proof for stability of the system?
Not really, in the sense that, I mean, the system itself, we're not touching the control action, we're not closing any loop, so the system is supposed that it's designed properly. We're simply counting on the fact that, given that we have a good enough regressor, the parameter estimator will be able to converge in the standard approach. And that's really the only thing that and also the discrete time differentiator is also like just differentiating a noisy signal. So there are like just the proofs of the method that ensures that we're able to reconstruct with some properties that, of course, in this case depend on noise.
Yeah. And the other question is that you used epsilon modification method for your estimation. How you choose that epsilon?
That's a tuning parameter.
Okay.
So that's definitely an additional complication that we have to decide. But in general, it's something that we can visually see on a real scenario, because if we see the plot, we can see that also in the non-faulty case, so the one on the left, we actually have already this oscillation. So by adjusting also online what this epsilon is, we can see the plot that is actually shrinking. So in a real application, we could try to tune it based on the online implementation already.
Thank you so much.
Very glad. Okay, short question.
Thank you. Enjoyed the presentation. I just wonder whether, do you know if the friction that you're looking for is in the hydraulic actuator, or is it in the mechanism, the linkage that rotates the blades, where the friction is?
That's a good question, in the sense that in general, in both. So both mechanical systems experience some friction. What we're interested in is estimating the one inside the cylinder, because we use it as an indicator of the oil starting to damage and leading to other faults. Of course, on top of that, there's like potential fault happening in the friction in the bearing, if this is what you mean. In this case, we didn't account for that. We assume that we have a preliminary knowledge of what the nominal condition of that friction is, and we just use it. So we exclude the possibility of like having a fault in there, because it's less interesting probably, at least from this perspective of condition monitoring. Probably more for fault tolerant control, the other one.
Thank you.
We thank it again, the speaker.
Thank you.
Okay, so let me commit to the fourth presentation. So Professor Simani will present a paper with the co-author Pim Lam, and the title of the paper is Wind Turbine Blade Monitoring via Deep Learning and Acoustic Aerodynamic Signals. Please, Professor.
Thanks, John, for your introduction. I can stay here. And well, this work is quite specific for the application. So it's an application-oriented study. And well, my visiting student couldn't come here, as I said yesterday, because of other problems with logistics and other issues. But so I accepted to present his works, which will be included in his final PhD thesis. And so he visited our university during an exchange program, and we wanted to test some methods. Perhaps the work is mostly focused on the a tool or a method for trying to filter out the noise from signals. Well, in this case, are aerodynamic acoustic signals acquired from a vertical axis wind turbine. I will show later. I will explain later why we are considering this data. And so, in my view, in order to provide a more general application example, I feel that this approach can be applied also to not only, as in this case, acoustic aerodynamic signals, but perhaps some vibration or other kind of data acquired from offshore or onshore wind turbines. So I will enter into the details. I will give a brief introduction to the problem. So the problem formulation, I will just recall very briefly the state of the art. So I will give you a description of the solutions that we provided and some final discussions. So in this paper we presented, well, the main contribution was provided by my students, the development of an efficient and cost-effective monitoring method. As I said, the most important step is in the phase I will show later in a while, robotic group. So they mainly use convolutional or deep learning, deep neural networks mainly for image processing. And at least in my researches, we are using shallow still the tools that we proposed, for example, at the beginning of the 2000, from 1998, when the first tools were developed, especially in the MATLAB and Simulink environment. So it's why after that a lot of works were motivated and started, because the tools available now, we have students that are working with Python, and everything is maybe more effectively also can be very easily implemented. But in this case, we propose, the students propose the use of a convolutional neural network, and again, another requirement, if you think, well, it's not specific for this application, but in general, you need a deep neural network that can be used for example, in an edge computing, which is an important keyword now in Industry 4.0. And so you need to reduce the complexity if you think of these devices that you are deploying, especially if you think of exploiting some FPGA specific hardware for implementing deep neural networks. Now there are some interesting works that are focused on this topic. So we are using mainly two deep neural networks. One is used for reducing the noise on the data, and the second one will be used for monitoring, so providing you the information that the system is not working properly. So the state of the art, normally wind turbine blades produce aerodynamic audio signals. They are contaminated by complex noise, where the noise can derive from very different areas, can be speech from people around, depending on the application area, can be other environment, more complex, we will see later. Normally, if you are using conventional noise reduction algorithm, you can incur in the problem that you are losing. For example, you are filtering out the fault information normally, especially, for example, in the linear case, you don't know in which frequency band the faults are acting, so maybe you cut off the main information you need. So sometimes you can use the data in an effective way, because in fact you cannot exploit them completely in their contained energy. Some data can be unprocessed because of the presence of the node. So it's important in order to increase the recognition accuracy, so it means the main outcome, so for example, the number of faults that you can detect. So it's important that you reduce the effect of the noise. So the solution, as I said at the beginning, we It was especially application-oriented because with, for example, I will show later the scheme. So a PLC was used in order to label the data. For example, in this case, the PLC can discriminate, or depending on the working conditions of the system, if, for example, a noisy device which was included in the system can produce noise, so the PLC can indicate if this sequence of data can be affected by noise. So this PLC can provide a priori knowledge of the presence of the data. So it's a first way of including some information of the data. Or on the other case, if, for example, a device which introduces noise in your system is not working, so it's not corrupting the data, so it means that the PLC can trigger the system and inform you that the data are very, they can reliable, so you can use them for full diagnosis purposes. So but of course, as I said at the beginning, this approach, this work is specific application-oriented, so it's why it works in this case. So we propose, well, the students, my students proposed a dynamic or the deep neural network for reducing the noise from the audio signals, and then by training a second neural network, it can be used for providing you with the information. So this is the complete scheme. So we have, well, here is shown an horizontal axis wind turbine, even if the data I will show you later, and also I will say to you why we are using the data, come from a vertical axis wind turbine. So we have here the system which includes the PLC. So you have here a condition monitoring, a first condition monitoring tool, which says that is the data, so is able to label the data and to say if they can be corrupted from the beginning by noise. And then you have the part B here, which is the neural network, which is used for as a sensor fusion tool, because I will show you later, we introduce some performance indices of the audio signal, aerodynamic audio signals that normally are used in speeches applications. So we are using these tools. And then we have a second deep neural network for providing you the information on the faults. So we have the part A is the audio collector and wind turbine operating data monitoring. The second is the noise filtering module, and the second, which contains the feature extraction, noise reduction, and signal synthesis, which are provided to the second neural network for diagnosing the wind turbine. So the audio collector, we have the wind turbine operating data. Of course, the noise cannot be effectively eliminated. So using, for example, a PLC, as I said at the beginning, PLC monitoring, we can identify, for example, specific audio sequences are not affected by noise. So we have an initial labeling of our data. So when, for example, you can also think of using your audio collector only, for example, if you know that the data are reliable. So in that case, the PLC is triggering your system and you are acquiring the data. Again, of course, is specifically oriented to the application example we are considering. Well, the noise reduction module it represents the focus of this work. Is considering different indices that, of the audio signals. We use some method to extract audio signal features. These indices are computed in the time, in the frequency, and in the inverse spectral domain. it was proposed to use a principal component analysis to reduce the complexity. So it's why I asked my student, why you didn't think of, why I said at the beginning, I'm not a super fan of deep neural networks. Why you didn't use a shallow neural network in order to understand if this task could be performed by a simple 3-layer neural networks, or I don't know, a radial basis function, maybe with the traditional multi-layer perceptron neural network, which is date back more than 20 years ago. So it's something that we need to, again, to check it. And so it represents an effective screening, efficient screening of the effective feature. So which kind of features we are considering in our audio data? So we have time domain features. I'm just recalling them, are provided by a paper which is mentioned in the references. They are specific features for the audio speech data. So short time average zero crossing rate, so it's the number of times that the signal passes zero, the zero value per frame. Short time energy, it represents the strength of the audio signal, representing a transformation of the signal amplitude. There are the second class of indices and in the frequency domain. So the short time power spectrum is again linked to the frequency, to the information contained in the, so in fact is the signal power per unit frequency band, represent the variance of the signal as a function of the frequency. And it represents the frequency range where this signal fluctuates more. And we have another class of indices which are represented in what we call the inverse frequency domain. So the Chepstrom domain's frequency feature, which is called a Mel frequency septral coefficients, is perceptual, so it's linked to the perception of the noise of the data of the speech. And another index is quite important because it's linked to the if you are able to make a prediction of your signal based on the past sample points. So it means that maybe if the signal is white, you are unable to use, or you are, again, providing a white signal, so it doesn't contain any information. So, and then after these three classes of indices, we propose a principal component analysis for reducing the dimensionality complexity of especially of these features, and to maintain the information as much as possible. And so this deep neural network was trained. Some details, technical details were included in the paper in order to implement the noise reduction problem. So we have this is the scheme of the general procedure. We have the data. I will show in the application example. We train this neural network. What it's using is not shown here. You can you can trim some data in order to, because we assume to have the noise-free data and the noisy data and also the noise source, so the disturbance. So we were able also to understand which was the best configuration of the neural network in order to filter out the noise from the data. So, of course, the data, the training of the neural network depends on the signal-to-noise ratio. So, in fact, there is a part of this scheme which is not shown here, is mixing the noise-free data with the noisy data and the noise source in order to generate the training data and to train the neural network. And then we have the third, well, it's a second, the third part of the scheme, which is the second deep neural network for, which is the network that normally should be with reduced complexity, especially if you think of an edge implementation that now is quite famous, quite important. It means that you need to have low complexity because you want to, for example, to implement it on a specific hardware, so you need to limit the hyperparameters of your neural network. So you need to, for example, to eliminate some cells in order to reduce the complexity. So the complexity reduction was based on two steps. The first was a first tuning of your hyperparameters, and then on the basis of the solution found on the first step, you proceed with the fine tuning of the weights of the neural network. So the simulation results we use, just to try to summarize briefly, we use some data available from the web. There are recordings of 5 major categories of noises coming from animals, natural landscape, and water sounds. For example, rain, because for example, if you think of an offshore wind turbine, maybe it's working. Of course, it's not the case of the application example. A second data set which contains voices from people, so voice bubble, factory noise, other channel noise, ping noise, various military noises is a standard database. And I don't know if no, it's not here. So the performance validation, it was used this kind of this data, and in order to also to tune our neural network, we have objective evaluation criteria. For example, the perceptual evaluation of the speech quality and the short-time objective intelligibility, which are some performances of the speech. And so the data that we used for our application came from a previous project. It was presented during the SAFEPROCESS 2015. The data were acquired from a vertical axis wind turbine that was mounted. It was a crazy project. We proposed to convert the energy coming from the turbulent wind produced by cars when these devices were mounted in the middle of the road. And so we tried to sell also this idea. And so we got some data, and we used them for just to try and to train our network. And we got some interesting results because we were able to, I didn't mention, so we produced, because these wind turbines were quite old, so we can damage them in order to introduce some specific faults. And we got some interesting results, and also the tool for reducing the complexity of the neural network was quite interesting, and it was working good, well. So just in order to conclude, so we produced, I proposed these works. It was specifically oriented to the application we considered. So it's it introduced one first module for reducing the uncertainty in the data, and then a second module for obtaining the information on the fault. And of course, now we would like to try to apply this solution to real test examples. Thank you for your attention. Sorry.
Thank you, Silvio. Yes. So,
thank you.
Time for just one short question or comment.
We can.
I don't know. Just in wind turbines, you are the wind turbines live different seasons and wind weather, different weather. So how to classify sounds according to the weather?
Maybe
it's
yes.
problem, yeah?
We have
Okay.
yes, it's true. We have we
You have
had
to-
some sources provided in the database, but of course we need to try to other simulations. It's good. We can talk later. Sorry for it.
Okay.
I was-
We thank
I
again
tried to
our
summarize.
speaker.
Thank you.
Thank you, Cindy. So let's to switch to the fifth presentation. So this will be presented by Federica Galli. And the title of the presentation is Current Sensor Fault Diagnosis of Wind Turbines using a standard gamma filter. It's an experimental validation. So you will present in a half of the authors.
Yes.
Yeah. You can, I think it's...
Thank you very much for the introduction. Good morning, everyone. Yes, indeed, today I'm presenting the work of a colleague, another PhD student from the IRSEM Research Laboratory, Mohamed Abbas, who could not attend the conference. The topic is about current sensor for diagnosis for DFIG wind turbines using extended Kalman filter experimental validation. So I'll start with a quick description of the context and the introduction. Then I'll explain what is the problematic, so the problem that this research wants to address. And then we will see together the modeling, the diagnosis approach that is proposed, and some experimental results. So wind energy is today one of the most developed kind of sustainable energy. There is a series of factors that is pushing toward this direction, like the limited fossils fuel reserves, or the fact that there is a higher and higher demand in energy production. The Global Wind Energy Council published a report in 2023 that showed that that is the best year on the record for wind energy. They recorded total new capability installations of 117 gigawatts, which is a 50% increase with respect to 2022 and involved more than 50 countries globally. So this is really a sign of how wind industry is seen, at least today, as a key solution for sustainable energy production. Now, wind systems have been on the forefront of significant advances in control, in diagnosis, in supervision systems, and they function. So the monitoring systems are provided especially with current sensors. These current sensors are essential for their correct monitoring of the system, and this is why the present work is focusing on this. So sensors are subject to failure. They have to work, in this case, in harsh environments with electromagnetic interference. So the idea is to avoid control instability and system malfunctions. Now, the problem that is addressed in this particular research concerns the design of a diagnosis methodology to correctly detect and locate faulty sensors on the wind turbine rotor. Now, in literature, in this field, we have three different families of diagnosis techniques. We have signal-based methods, data-driven methods, and mathematical model-based methods. This work focuses on mathematical model-based method, and what is proposed is a model of the DFIG, so the doubly fed induction generator, coupled with the Kalman filtering. So the idea is to use the Kalman filter to help the detection and localization of simple and multiple faulty sensors. Now, in this slide, you can see the general scheme of a wind power system. You have here the DFIG, which is the main objective of this work modeling. And then you also have the rotor side converter and the grid side converter. Now, here you can see the model that is proposed. It's a state space model that takes into account some nonlinearities, especially coming from the fact that the wind turbine rotational speed depends on the wind speed, which is not constant, it varies. So these effects are taken into account in the model. You can see here the state variables, which are the currents of the rotor and the stator in the imaginary reference frame, and the input is the voltage. Now, the proposed method has the scheme you can see here. You have the model here on the top in the middle. Then we have the control input, the voltage, and in the output we have the sensor measurement. Now, all these informations are given to the Kalman filter, which is an extended Kalman filter. And after the use of the Kalman filter, we can move on to the localization and to the display of the results. So the proposed Kalman filter is an extended Kalman filter because it's a nonlinear system. So first we discretize the system, then there is a linearization with the Jacobian, and then finally we arrive at the Kalman filtering with the classical prediction and update phases. After that, we move on to the fault localization. So what happens is that, as I said, the model computes the current in the imaginary reference frame, which, as I will show later, is not the optimal one for this kind of tasks. So the current is transformed with the Planck transform into a real reference frame, here noted as ABC. And once that this is done, it is possible to compute the residual. So you can see the residual between the computed current and the estimated current by the Kalman filter. Now, the proposed methodology was applied to experimental data set. You can see in the picture the prototype used as test bench. It is provided with a DFIG that you can see here, coupled to an asynchronous electrical motor that is behaving as the wind turbine. And what was done is that the collected data from the test bench was modified, and they injected some biases in the data to simulate the sensor faults. Now, in these two graphs, you have two different faulty behaviors. On the left, you have one faulty sensor, and on the right, you have two faulty sensors. You can see here in the rectangle the faulty behavior. Here we have the yellow curve that is exceeding the healthy measurements, and here you have the purple and green plots that are exceeding the healthy values. Now, if we look at the current in the imaginary reference frame, what you can see is that the yellow curve, which is the estimated current, and the blue curve, which is the measured current, are quite similar, quite close to each other in healthy behavior, but they are quite far when the fault appears. Where is the issue? That here you have on the top the rotor current, and at the bottom the no, it's the two components in the in the imaginary reference frame, and as you can see, all of them are affected by the fault. So yes, we can see where the fault starts and ends, but it's really difficult to locate it. So this is where the Kalman filter comes in, and once that we arrive at the end of the methodology and we compute the residuals, we can see that it's way easier to locate the fault because we have three-phase current and we can directly see what is the residual that is affected by the fault. The coupling between the variables is not there anymore, so we can detect and isolate the fault at the same time, in real time, in a precise way. So to sum up, the proposed model is based on Kalman filtering. Kalman filtering is used in this case with a different reference frame from classical approaches, which is a real reference frame. And the fact that the transformation is applied to change the reference frame allows to use a single Kalman filter instead of moving to other approaches like generalized observer schemes or dedicated observer schemes. As future works are concerned, the authors would like to expand this application to other kinds of data, like the data coming from speed sensors, and not just current sensors, and also maybe try to use it to detect and localize electrical and mechanical faults in the system and not just in the measuring equipment. Thank you very much for your attention. I can try to take a few questions. Well, I can try. I'm not sure I have the answer, but...
We'll have some time for remarks or questions.
Yes. I will make sure to pass the information to the authors.
Okay.
Hi, I think you did a really good job presenting that,
Thank
considering
you.
it's not your work.
Thank you very much.
And so I'm not sure this is a question, more of a statement. It seems to me that you've got these three current sensors, and the magnitude of the current, the RMS current, on the three of them should be similar, because a good model of one phase is the phase that's right next to it. So.
Yes.
Am I oversimplifying things to think that you could just compare the RMS of the three sensor signals, and if one of them sticks out compared to the others, there's a fault?
Maybe. I will write it down. I work in a different field, so I am not an expert on current sensors and wind turbines. But yes, indeed, it could be an interesting approach. I will pass on the information. Yes, thank you.
Thank you very much.
Last remark.
I appreciate you might not be able to answer this. This is, I guess, a more general question, but do you know if it's possible to differentiate between if it's a fault on the sensor itself or a fault on the actual phase?
Well, this is a good question because it's not easy in any field, not just wind turbines, to know if the signal you have is varying because the system is damaged or because the sensor is not working. So I think what they're doing here, it's kind of, it's interesting because it tackles directly the sensor malfunctioning. I don't know if this specific approach could be applied to mechanical faults. I know they are thinking of it. What I know is that Kalman filtering is also used for mechanical faults and these kind of things, but it's really difficult, and sometimes it's also based on the experience you have with the system. You just know that it can break in such a way, and
information, right?
yes. Yeah.
Thank you. You did a fantastic job presenting something that's not your work.
I did study the article before today.
Thank you very much.
Thanks.
Thanks again, speaker. Thank you. So now we have the last presentation. Yeah, we have a few more minutes.
Yeah.
I can introduce you. Is co-chair, my co-chair, the co-chair, John Martinez Molina, who is presenting the paper evaluating the effect of control gains on wind turbine drive train deterioration, an experimental study.
Thank you very much. I will start now, okay? Even 1 minute
Why not?
before the time. So, this work was prepared by Elena Romero. Yes. Yeah. So Elena Romero is my PhD student, together with Christophe Berengue, present in this room. She finalized the thesis in December, and she worked in the wind turbines pronoxis and decision making after pronoxis. So the idea was to use information about the functioning of the wind turbine in order to reduce fatigue or deterioration, in particular in drive times. Okay, so this is an experimental study linked to the previous papers related to that topic. So for all people here, probably it's obvious that the drivetrain is a very critical system in the wind turbines, and normally we have to be care with the health of that component. One of the important sub-components in the drivetrain is the shaft and the gearbox, and of course we can probably modelize that like a simple model in order to check if the health of the drivetrain is good or not. So this is very important because we have a trade-off between conversion of electricity, right? So the level of electricity that you convert, and this part is really linked with that conversion. This is in the chain of the energy conversion. So in wind turbines, in fact, because wind speed is not constant and depends on the season, you have different aggressivity of the wind. So the wind speed can change a lot, and according to that aggressivity, you have some torsional stress in the components. So particularly in the transmission systems, you have some angular deformation, angular torsional angulars. So in fact, we have confronted to a dilemma: is producing maximum energy or reduce the stress of the system. And we asked the question for several years ago, saying that what I have to do is sometimes hate using a controller that is not optimal in the electrical point of view, energy point of view, but what we lose if you do something different. So this experimental experimental studies try to answer some questions about what kind of good decision we have to take if we have some information about the aggressivity of the wind speed. So my talk is organized like that. So I present a little bit the drivetrain model that we use, the nominal maximum power tracking that we consider in this study, the lab prototype that we use to the experimental study, and some conclusion and future work. So in fact, we consider that the transmission is like a flexible system, and because it's a flexible system, you have a stiffness and a damper. And this particular model, we consider a damper that is also a function of the angular torsion. This is used. Some models are used in for mechanical engineers that consider that some efforts in the damper also depends of the angular deformation. So this is in fact a LPV model. It's linear parametric variant model. So it's not completely linear. And the inputs that you check here is the torque of the rotor coming from the wind speed. So it depends on the wind speed force. And the torque produced by the controller. So in blue is the torque provided by the generator that you can modify. So of course the first input is completely almost random. You don't know nothing. It's impossible to predict. You have to make it with that. But the torque from the controller, you can modify a little bit. So this is 1 degree of freedom to modify the functioning of the wind turbine. So in terms of maximum power tracking, so we have to close the loop. So we use the torque of the generator, so the equation 2 here. And one of the popular methods of MPPT methods is to control the torque of the generator proportional to the square of the rotor speed. And the gain, this proportional, this K up is, say, to be optimal in terms of maximizing energy production. Okay? So, and normally this gain depends of parameters of the wind turbine. So the radius, and so on other parameter that is well known. Okay? So this is the theoretical one. And this means that the wind turbine will follow the wind speed. So depending on the variation of the wind speed, the blades rotation will change according to the wind speed. This is the equation 4. So in fact, modifying the gain means that you modify lambda in a little bit. So this is a small modification, more bigger scale or less bigger scale, you modify lambda, and of course you modify the operating point. So, of course, if you are far from the optimal one, normally you produce less energy. So this is a priori knowledge of the system, right? So the question is probably, or the problem is, what have to do? Increase the gain or reduce the gain? What is the good solution to reduce the stress of the transmission system? So in this paper we are interested in that. So we vary the gain and we check what happened. We test in an experimental test that we built in the gypsum lab, Grenoble, and we compare the produced energy and the losses in the transmission system. So the dissipated energy that we consider that is an image of the deterioration of the transmission system. So let me present the lab prototype. So this is a prototype built in gypsum lab with our engineers. It's quite amazing. We have several units like that. So 3 units for teaching, 1 unit for research. So it's quite amazing. And if you look in the picture, you have a fan that produces wind speed, so we can vary wind speed. And we have a wind turbine that is probably much better in this picture because you have 2 blades wind turbine. Okay, so this is quite amazing because we use helicopter blades to produce a wind turbine. And this is also interesting is we produce 2,000 milliwatts. That's to be big. So using 32 centimeters of blade radius, diameter, and the wind speed can change between 0 and 5 meters per second. And of course we can produce several kinds of wind speed. Yeah, this is interesting. Some people say that we can also put some humidity to change the density of the air. For the moment we don't touch that point, but it's possible in the future probably. So the system, in fact, we can modify the voltage of the fan, so producing different wind speed. We can modify the pitch angle. This is quite nice also in this small platform. So we can modify the pitch angle. So we also can test the impact of the pitch angle in the transmission system behavior. We also have a loop for the electrical current. So we control the torque of the generator, and we can compare the reference and the real one. So we have that information, and we have of course the velocity of the rotor, and the transmission here is really a little bit rigid, right? It's so rigid that it's not interesting for us in our study. So Elena imagined a system where we put something more. So the wind turbine is real, but we simulate the transmission system. So we have just added a dynamical system that modelizes the transmission system, and we put together with the real system one, okay? And we run the wind turbine with different wind conditions. And the important point here is that we measure exactly what happened in the transmission because we have a model. And we can recover that information and compare the performance of the wind turbine in terms of energy production and the dissipation energy in the transmission system. So this, I hope this curve is easy to understand. I try to take time for that. So you have, for instance, here is an example of the experimental results. So you have different wind speed. This is quite aggressive wind speed. And we have tested different gains. So in fact, just let me imagine that. So normally, the big that produce more torsion, angular torsion, are the optimal one. And if you increase the gain, you have a little bit more torsion, but not a lot. This is quite similar to the optimal one. So in terms of torsion, angular torsion, there are no difference between the optimal and the fact of increasing the gain. However, if you decrease the gain of the MPPT system, you decrease the torsional angle. That's the amplitude. Okay. So in fact, this is probably more interesting because you only decrease 10% of the gain, and you decrease considerably the torsion angle. Of course, if you decrease a lot, you will pay the cost. Okay. What is the cost? In fact, is the produced energy. So in fact, of course, the optimal one produces the maximum energy that you are able to recover from the wind speed, and the other one, and the other gains, even if you increase or you decrease the gain, you always produce less than the optimal one. This is logical, right? And the question is probably the good answer of the question that I said before is the second curve, is the second figure, is what is the dissipated energy in the transmission system. And we remark that if you increase the gains, you will dissipate more transmission. Okay, so you increase a little bit the gain, and you will dissipate more energy in the transmission system. So the good way is to decrease the gain a little bit, and you decrease that dissipated energy. Of course, if you decrease a lot, like in a curve, you lose a lot of energy. So you can find a trade-off between energy production and deterioration of the transmission system. Right? So this experimental setup, we also perform some simulation, but this experimental setup is just to illustrate what happens if you modify the gain of the feedback in terms of fatigue or stress, mechanical stress of the transmission system, and what is the good direction to take, okay? And in fact, one of the conclusions is that we have to adapt the gains according to the weather conditions. And today, most of the turbines use same gain during 10 years. Same gains. It's never changed, in fact. It's really very conservative. So industrial and wind turbine are very conservative, it's the same gain. Probably because I discussed with some industrials say that we operate in the suboptimal one, just to preserve the transmission, okay? But we never know exactly what we lose, in fact, okay? And in particular, if we adapt the gain, probably we gain the lifetime of the wind turbine with good performances. So in a second PhD thesis, Monica performed a second thesis on that, we asked the question if the wind turbine can be adapt the operating of the system in order to modify the lifetime, the remaining useful life of the wind turbine, in particular the transmission system. Okay. So this is the main results. So just let me conclude with some words. So we have presented an experimental results of wind turbine subject to different torque control gains. The drive time have been simulated, as you remarked, and we have obtained information about the angular deformation, power dissipation, generated power, in order to establish the trade-off between mechanical stress and energy production. In the future works, we expect to include variation in the pitch, probably independent pitch, but this platform is quite difficult to do independent pitch angle, but at least variation of the pitch angle in order to evaluate the impact of the pitch angle variation, a small variation, in order to reduce stress in the transmission system. Thank you very much for your attention.
Thank you, John, for your presentation. And yes, Aaron, thank you.
Thank you very much, Philip. Very interesting. You really started off talking about Region 2. Yes, I tuned a bit. And actually, you're talking about the
constant pitch,
tip speed ratio and so on, and the optimal for the design of the in terms of rotor speed. But actually, my knowledge of this is that majority of the very big changes in torsion occur in region 3. I showed some slide the other day of a 5 megawatt wind turbine simulation, and you know there's a good 5% variation when you have a lot of flat bias bending and so on going on. So my question is this: how capable is your experimental model able to really properly take account of region 3? You mentioned going into
we can work also in region 3.
Yes, but you're not really handling region 3. You're modeling region 2, in my view.
Yeah, the controller is in region 2, right?
Yeah.
But in region 3, you normally have a speed control, right?
Yeah.
Just to maintain the power in the maximal value. So we can do that in just controlling the pitch. So in fact, in my opinion, you have two problems. In region 2,
always
you have 2 degrees of freedom to reduce fatigue in the transmission system. You have pitch probably and the torque of the generator.
Yeah.
But the second one, so in the region 3, you allow only the pitch. Right? So you only have to control the pitch because torque is around the nominal speed. You cannot. This is not a degree of freedom, no more. So the torque is constant. Right?
But my point is it's probably a simpler problem to handle in region 3, but it's a more severe.
It's more severe. I agree with
you.
It's probably more severe in region 3, and probably the wind turbine works more time in region 3. Probably, yeah. But of course, this is just how we can win in region 2, okay? And probably that is a first study that allows us also to put the question, or to say, if using pitch and torque in region 3 is possible to reduce fatigue? This is a good question probably in the future.
Yes, it is. But removing the asymmetric loading is the key to all of it, because that's causing effects in the drive system, of the hub, and it's all intercoupled.
Thank you.
Just a comment for those who are not familiar with region 2 and region 3. I don't know if anybody knows that the region 2 is the partial load, region 3 is the full load condition. Yeah, 12, 15. And in region 2 we are using the torque control. In region 3 pitch, and in region 2 pitch is not used. So just to remark, because also there are different terms depending on if you're using just region 1 or region 2. And if there are, yes.
Thank you very much for a very interesting presentation. You mentioned that you are investigating the possibility of adapting the controller gains with respect to some predefined lifetime. First, do you mean it as some sort of like online adaptation, or some sort of like planning ahead and having some sort of lookup table?
Both, in fact. So the best, in my opinion, is to adapt online according to the class of wind or with weather condition. So one of the work of Elena proposed a gain scheduling controller, so changing the gain properly according to the wind speed and weather condition. So we suppose that weather condition is classified, and according to the class of weather, to use the good gain. So Elena works in the control point of view, and we suppose that the classifier work well, but probably we can imagine I don't know, advanced techniques to establish that classifier and use the control that properly close the loop according to the weather condition. So the second point, if I answer the first question that you propose, is like a lookup table, right?
Yes.
So, of course, yes, you can imagine a lookup table offline. You optimize. So Elena proposed a second paper linking to that. So it's a lookup table, you optimize offline, using several kind of wind speeds, even in simulation. So you can probably run a realistic simulation, calibrate the gains, and then in the real life, you just run the lookup table. Okay.
And just a small follow-up, in the case of the online adaptation, Do you think that instead of adapting with respect to a desired, let's say, lifetime, would it be possible to adapt it given a lifetime according to a trade-off between power and fatigue? In a sense that
of course.
the turbine is really new, we can stress it, but after a couple of years when we can...
An important point is, probably there are not the question here, but when you apply this torque in a second order system, because it's like a mechanical point of view, for any K, the system is stable. It's because that this MPPT is very popular, because it's always stable, even if you produce nothing, okay? So it's always stable. So you have the degree of freedom of changing the K, up to you. So our idea is to, and with this stuff, we try to imagine a health-aware control. Let's say a health-aware control, I would like to work during 10 years producing the necessary energy, probably not the maximum, but to guarantee a lifetime of the wind turbine. So you can modify the gain a little bit every day to achieve that remaining useful life. So this is, for us, it's really a point. So Monica, for instance, working in modifying lambda a little bit, modifying K, modifying lambda. So modify lambda or K in order to guarantee some future behavior, future function of the wind turbine. So the remaining useful life is a random variable, but we expect to control that variable by that control loop. There is not the same time scale, right? Because you have to control something that is expected in the future. Okay.
Thank you.
Okay.
Any other comments or questions before closing the session?
Just to, it's a control of the control, right? You control the turbine, and the remaining useful life controller control the remaining useful life, like modifying some parameter of the controller. So
yes, Ron.
I want to pick up what you said very quickly. Wind turbines are almost never tuned. The offshore ones are pretty good, actually. The ones on land are just a waste of space. Half of them are off. They never go to the field to do anything to them. The maintenance on them is very poor, and yet our governments are shouting out wanting more and more on land wind turbines. It's absolute nonsense. Most of it comes from the sea.
Okay, thanks, Ron, for this last comment. Okay, we are going.
Okay,
my
thank you
co-chair
very much.
and I. Thank you. Let's thank again the speaker. And we are closing now the session, and you have a lunch break, and then after that, the last keynote speech at 1 o'clock. Thank you.
Okay.
Okay, thank you very much. Welcome to this session here for the detection and isolation of linear systems. My name is Henrik Niemann, and I will be the chairman. I will be the chairman for this session here. The first paper is already here, and it will be presented by John Martinez. And the title is Novel Model for Diagnosis, Prognosis, and Health-Aware Control of Lithium-Ion Batteries. So, please go on.
Thank you. I think there is a microphone for the questions more later. Okay. Okay, thank you very much to be here at the beginning of the afternoon. So I started my presentation. My name is John Martinez. I am a professor at Grenoble Institute of Technology. This work is a collaboration with colleagues in Chile, Universidad de Chile, and the AMES Research Center of NASA in California. My colleague Christophe Berenguer from GIPSA Lab at Grenoble, and Monica is my PhD student that is now working at that topic and finalizing the thesis. So this work is related to the modeling batteries, lithium batteries, and is intended for diagnosis, prognosis, and in particular health-aware control. So mainly we are focusing how controlling the lifetime, the useful lifetime of batteries. So of course it's well known that batteries are present in many applications, and in particular in electrical mobility. So it's very important to manage the lifetime, the useful lifetime of batteries, and the main idea is how obtain the ways to manipulate the way where we operate the battery in order to change the remaining useful life. So suppose here in this course, the first one is batteries that dead randomly, so you never fix the date of death of the battery. In the second one, you suppose you control the system operation, and you can fix the date of death of the battery. So the idea is really control, even if it's a random variable, so you control the remaining useful life of batteries for a battery or for a family of batteries. So the idea is take into account that for optimally scheduling maintenance. For instance, if you have electrical vehicles, so you can exactly fix the date of the maintenance of the vehicle in order to change the battery in a good time. The second point is, for instance, reconfiguring the system, so the way you operate the system in order to use the battery in a good way, in particular before it fails. The third point is prolonging the battery lifetime, but modifying the way we use it. So we have a different alternative for that. And the last one is, imagine that you have a plan, optimally planned at the beginning, but you have to replan it according to the real situation the battery are suffer. Okay? So let me show you an example. So you're starting from point A to point B in an electrical vehicle or electrical bike, and you decide the trajectory that you follow, so the path, according to the state of charge of the battery. Okay, but also with the state of health of the battery. That is dependent of the trajectory, you will fatigue the battery more faster, and probably you don't have guarantee of the total lifetime that you expected. So the idea is that you correct every day, and you select every day the different path according to a reference to a pre-selected date of death of the battery. In terms of battery technology, lithium-ion batteries are mostly moderated by electrical circuits. So the main important point here is that the hypothesis is that you have internal voltage, so the open circuit voltage, and the internal resistance that are nominally dependent of the state of charge. That is well known in the literature. So here we will focus in that hypothesis, and an important point is both depend on the state of charge, but in particular the resistance increase when you discharge the battery. And in addition, that resistance normally increase with aging, and that is an important point in establish the aging of the battery. So this curve, for instance, is an example of a battery, the same battery discharged and charged many times. This is just the charging curves. And you have this charging is different according to the age of the battery. So more age have the battery, more faster you discharge the battery. Okay? So this is well known. And in particular, the time that you have energy, this is called the capacity of the battery. So you have ampere hours available in the battery. And if the battery is aging, you have less ampere hours to be used. Okay? So the main hypothesis in that model is that increase of the resistance and the decrease of the battery capacity are correlated, and that correlation is modeled by gamma. So this is a parameter that models the aging of the battery. And all sources of aging, all sources of fatigue of the battery are condensed in one parameter. So just to simplify the problem in looking for one parameter that models the aging of the battery. So this hypothesis is very important here because you will remark that simplifies really the problem. So in this case, for instance, if I take the electrical model of the battery, you have the classical Coulomb counting. You count the number of ampere hours that you use. That depends on the parameter C. This is the capacity of the battery, but this is the nominal one, divided by gamma. That's the parameter that models the aging of the battery. The voltage is also modified, normally modified by the internal resistance. I modelize the nominal one, multiplied by gamma, that modelize the aging, I said before. And in fact, this model is really a linear parameter variant model because many of the terms depends on the state of charge. Okay? If we focus only in the thermal model, so the temperature depends of ambient temperature, of course, but also of the Joule losses. And Joule losses depends on the internal resistance of the battery that change according to the aging of the battery. So gamma also appears in that equation. And this is an interesting point because in this work, we don't use temperature as useful information, only just for validate the model. So temperature here is just to illustrate the power of the model to predict the aging of the battery. So summarizing the model in a compact way, you have three states. So theta is the state of charge. Vt is the voltage in the terminal that you can measure. And T is the temperature that really we don't use for estimating the aging of the battery for the moment. So important point is that the equation 5 says that the states are linear, dependent of inputs that depends on the state of charge, theta, and the external temperature, but also of the applied current. So according to gamma, we can imagine in the future, modify the current to modify how the battery will be fatigued or deteriorated. Right? So this is a degree of freedom that we can use in the future. So this is a simulation. So we simulate, for instance, a new battery. Normally parameters are calibrated for the new battery. So we take a battery at the beginning, you obtain a nominal model, and after that, the problem is how estimating the degradation of the battery. So this is gamma is equal to 1 for a nominal one, for a very new battery. So any deviation of gamma means that the battery is more older. Okay? So in this case, we can use the model to estimate gamma. Okay? And how we can do that? Because we have measurements about the voltage or temperature. Here we use also only voltage. Okay? So we recover voltage from the model, so V hat, compared with the voltage measured in the terminal of the battery. This produces an error. This error is used to update the estimation of gamma. Here we use just a PI estimator. This is just integration of the error. Could be a proportional integral controller. Use it as like an observer, right? But it's an observer that observes one state, gamma. We don't need to estimate other parameters. We use directly the model. So only we focus on obtaining gamma based on the model that is calibrated for the nominal model of the battery when battery is new. So gamma will reflect any modification of the aging of the battery. So we recover data, real data from the AMET Center and NASA, and this data concerns many scenarios of the battery. We only, in this paper, chosen some the charging scenarios and some intermittent pulse scenarios, okay? So if you discharge the battery, this is quite easy problem, in fact, to estimate the capacity reduction when the battery is aging. But it's good for illustration that the model is good for predicting that behavior. So here you have the same battery at different aging, a different level of deterioration. So when battery is new, you have the red one curve. So in fact, you have the black are the real data, and the color are come from the model. Okay. So the green one predicts that battery is new. Okay. The blue one is in the middle life, and the red one is really very old battery. So of course, as I said before, when you lose capacity, amperes hours is available in time in the battery, this means that the battery is more older. So the problem is, okay, it's well known, the model follows that, but now we have some information that are not really available in real time. So the first one is the state of charge. So the second, in fact, the second figure. So the state of charge is how much charge you have. There are no sensors for that. You have to count numbers of amperes, okay, per hour. And the first curve in the top is the estimation of gamma. So the parameter that we use to modelize the aging of the battery. So when gamma is equal to 1, you have a new battery. But this is just a reference, you know. You take a battery, you establish your new battery for you, and then you compare any battery. So of course, you can obtain, from a family of batteries, you can obtain some battery are more new than the new one, okay? So this is, for instance, the case. It's like a battery that is better than the new one, okay? But after a certain time, you have, for instance, in the blue one, the battery aging, so the gamma increase. And more older is the battery, gamma is more higher. So this is a way, in fact, very easy way to estimate the aging of the battery, only using one parameter, okay? And no information, just current and voltage. The second scenario is pulses in the current. And I use that because it's just to compare with temperature. So here, temperature, we never use the temperature to correct gamma, okay? But we use the same estimation to check if temperature is well predicted. And it's surprising that in black you have measured temperature, and in red one you have the estimator using the model, just correcting gamma. And you observe that when battery is new, in the left hand, you follow the variation of the temperature. Only the error is 1 degree. 1 degree error, and it seems it's just one degree of the ambient temperature. That is not possible to correct better than that. Okay? And the second one is when the battery is more older. So we remark that temperature is much higher. And similarly, as previously, you have just an offset. And this offset is constant offset, is a bias that depends only on the ambient temperature. That is not considered here. We never measure. Okay? In terms of gamma, in both cases, you have the new one that is close to 1, even if during the time which you discharge the battery is not exactly equal to 1. You have some variation around 1. This is probably because the model is not perfect, but it's a good indicator that the battery is probably new. And the second one is the battery is more older, and you check that the gamma really increased more higher. And so this is the proof that gamma, one parameter is enough to estimate the aging of the battery. And of course, the problem now is what happens if you have some scenarios when you charge and discharge the battery randomly. Okay? So in fact, we have tested that. Is the subject of a new paper with more details, probably a journal one. But the idea here is exactly the same. It's update gamma for a nominal model and take into account nominal behavior and deviation of the nominal behavior with respect to the aging battery. In the future, we have also the fact that we will probably design an observer, full observer with all states to improve the estimation of the states of charge. Because there are, of course, there are probably some errors that we cannot detect today. But the goal, if the goal is detecting the aging of the battery, this approach is enough. in some way. As you can remark probably, the fact that the model depends on gamma like an input, this means that I can use the model to predict the future of the battery, right? And we can predict how the battery will age in time and probably take decision how operate the battery to modify the remaining useful life. And because we can do that, this means that we can imagine designing health-aware controller for the battery. And in that case, this means that in the future, you buy a bicycle with a battery, and you are guaranteed that the battery will work during 3 years, more or less 1 day, okay? Because you control every day the operation of the battery in order to guarantee the total lifetime of the battery, okay? So this is the main goal, and this is the goal really of the model. It's for diagnosis, prognosis, and health-aware control. Okay, thank you very much for that.
We have time for questions.
Is it working?
Yeah. Some questions?
Yes. Yeah.
Thank you again for very interesting presentation. I just wanted to ask, the parameter gamma is something that you can have, let's say, absolute metrics to check whether the health of the battery, or is it something that you will have to get some value as a nominal value and then you compare it just to that?
Yeah. It's because it's equal to 1 new, because in fact it's like the battery, when the battery is new, you have a nominal model, okay? So gamma is equal to 1 because it's a multiplicative parameter, right? Like an input and affect in a multiplication. So gamma, in fact, nominally is 1. And the key issue here is because resistance increase and capacity decrease, the tricky was to use gamma, like just how much that resistance and that capacity increase and decrease respectively. And probably the hypothesis that is quite hard, but at the same time is useful, is say that both behavior are related by gamma. So this is quite new, because no people is not battery people experts say, oh, it's strange, but normally you find that behavior, and we use that behavior to focus in one parameter instead of two different indicators of aging of the battery. Right? It's more challenging because find two parameters with same amount of data with same model is quite hard. If you have a half of the parameters, one is more easier, and this is an example of the results show that the estimation of gamma is more easier. Right? Thank you.
Other questions? Seems not to be the case, so thank you again.
Thank you.
Stand here, else you cannot hear. Yes, the next paper is vector-based fault isolation by myself and Niels Kølsted Poulsen. It's a theoretical paper. I will go through. I don't know how many that knows Niels Kølsted Poulsen, but he actually passed away last weekend. So it's a little bit strange to stay here and present this. But anyway, I will start with a motivation example. That's a well-known four-tank system where it's controlled by two PI controllers. Measure the level in tank number 1 and tank number 2, and they control the pumps to the system. There's a number of faults in the system. We have included in the system the outflow of the 4 tanks, the pumps and the valves that could be changed. So And we have set it up in a non-minimum phase configuration, just use the controller from the original paper, and then look at what's going on in it. So the first thing is just to make a simulation. We are only making linear simulation. We are not including disturbance. So everything should be quite nice. So what we are doing here is making a simulation where we first step at tank number 1 at 500 seconds, and then at 5,000 seconds we also make a step change in the level of tank number 2. And everything looks nice, no steady state error, we are using PI controllers, nice control inputs. So that's worked nicely. Then the next thing is we actually introduce a fault. We are changing the valve number 1. And what we can see is that, of course, the result of the system is actually compensating for the faults. There's no steady state error in it. And we have also put in a residual generator, standard observer-based residual generator, and it's showing here. So the fault occurred at 2,000 seconds, and you can see immediately we get residual signals different from 0. But what is the interesting thing here is that when we change the operation point, the residual vector actually changed. So the positive one get negative and the negative get positive. So that makes it a little bit difficult to isolate fault based on something like that where it's depend on the operation point. So that was our motivation for looking into a setup where we take care of the input or test signal that we have included. So what I shortly will introduce to you is a double residual generator that was also presented at the last SAFEPROCESS, and some reviewer pointed out what is new in this paper. I think there's a lot of new things. So what we have here in the paper is we have a system with a disturbance input and a control input. We use a 2 degree of freedom controller, feedback controller, and a feed-forward controller. The feed-forward controller can be organized in different ways, so it's actually the reference could be reference input, it could also be an auxiliary input, putting in different places, just a matter of selecting KR in a suitable way. Theta is a multiplicative false, parametric false in the system, and the system depends on these faults here. So a little bit of theory, co-prime factorization of the system and the controller, the double Bézout equations and the Bézout matrices for it. It's standard, and as long as the Bézout equation is satisfied, we have a stable closed-loop system. So, but the last one here is an important one, Z tilde, that will be used in a short moment. So the double residual generator is just developed by taking this Bézout matrix here. If you look a little bit about it, then you will see the last part here, epsilon. That is our standard residual generator, now written in terms of the co-prime factors. But it could be generated by an observer or anything else. So the other one is the what we will call the dual residual vector. It's actually the residual vector for the controller, but we assume that we know the controller exact. So what is this one here is doing? If we look a little bit here, we have put in the double residual generator here, get alpha and epsilon out. And let's do the calculation. And the two residual vectors are these one alpha, depend only on the reference input, the input we come to the system. So it's no, and we calculate it exactly. The other one epsilon depend on a S of theta, and then you can see we have exactly the same part here again, V tilde kr and times r, plus something coming from the disturbance. So actually what we can write up is that epsilon is S of theta times alpha, plus the part coming from the disturbance. Going a little bit further, so then we have actually separated our system into these two parts here. S of theta is what we will call the fault signature matrix. It has the things that it's actually 0 in the fault-free case, or if our model and the system match each other, then it will be 0. So it's quite easy to detect that we have a fault, so it's just to look in epsilon to see if we have a signature from the input, alpha input. But we can do more than that. We also want to make isolation of it, and it requires a little bit of rewriting of it. I have not put all the details in this presentation how we can rewrite it. But actually, if we have a single fault in the system, then we can write it as shown here. SP bar is a matrix. It's known. We can calculate. Theta p bar is a scalar one depending directly on the theta p, one single fault. It is a scalar. So what we can do is we can calculate and estimate here always means that we can calculate the last part, and it is a deterministic part we can calculate. So we have the direction for the residual vector, and then we can compare it with the correct with the measured residual vector. So what are we doing? Well, we measure the residual vector and then compare it with the direction for the residual, the parametric fault that we will know that occur. So you get something like this one here. You have measured a residual vector, and then you can calculate all the other ones for the different faults and compare it and see which one is of them are parallel. So we just use the scalar vector product to see, and it's given here. So just see when this cosine function is close to 1, then we of course have isolated the fault, and then of course we can introduce a threshold, see how close should it be to 1 before we say we have an isolation of it. But we can do more. Of course, we have disturbance in it in the system, so therefore we can calculate the confidence interval around the measured residual vector, and then calculate this and redo it again. And then we take the expectation values of the residual vector, and we can do further, because we might have uncertainty in the system. So that will be a circle of our starting point here. So if our residual vector or our our residual vector is too small, then we cannot say if it's come from uncertainty, variation in the system, or fault in the system. So it will be also limited by that way. So we are able to build in both disturbance and uncertainty in the system in a systematic way. Just to mention a little bit about how to implement it, you can implement it in the state space. If you have a general controller, I get set tilde. If you have an observer-based controller, I have also given set tilde here. Quite simple. So it's quite simple to implement this. But compared to a standard residual generator where you use an observer-based feedback controller, you can get the residual vector out directly. This cannot be done here. The dual residual vector cannot be taken directly from the feedback controller. That is something the co-prime factorization of the controller. You're using the inverse co-prime factor in the controller, but we need to use the co-prime factor directly, and it's not included in the feedback control. So anything, a little bit back to the example, 4-tank system here, where I have pointed out the different faults that we can have. And then we have calculated S bar for these 8 faults. I have only calculated for the constant part of it. Of course, it has dynamic in it, but to make it simple, I've just calculated the constant part. This means that we might not be able to isolate the fault before the system is in steady state. But we get these 8 elements, and what we can see is, among other things, that if we have fault at the outflow tank 3 and tank 4, then the S is equal to 0, S3 and S4 bar is equal to 0, means that we are not able to isolate this or see it in the steady state. And that's also clear that the residual vector disappeared in the steady state. So let's follow what we are saying. Another thing is that if we have fault at the outflow at tank number 1 and tank number 2, then we are actually able to isolate the fault just looking at the 2 residual signals, because they will be separated. If we have fault at tank number 1, then we only have something in the residual signal 1, and the other one will be 0, and for tank number 2. So these 2 we will actually be able to isolate directly. But the other ones, you can see there are cross couplings in them, and so that's how it. Maybe I should say that the reason why there's a decoupling between the 2 residual signals in connection with fault 1 and 2 is that we are using a CISO controller. If we have used a min mode controller, then everything has been mixed up, and then we'll not be able to. So let's look again at the parametric fault here at the valve number 1, where we have changed it 25%. And what you can see is we introduced the fault at 2,000 seconds. We have first step at 500 seconds, nothing to see. Fault is introduced at 2,000 seconds, and then we are stepping again in 5,000 seconds. And you can see we have 1, or maybe you are quite clear to see there's actually 2 faults coming here equal to 1. Actually we have a fault number 5 and fault number 8 on top of each other. So with this combination of fault and input signal, we are actually not able to isolate fault between fault at valve number 1 and valve number 2. So they are here. Another thing I think you might need to note is that the system is first in steady state after the second step. 1,500 seconds after this will mean 6,500 seconds, but we have isolated the fault a long time before. It's actually quite quick. So the dynamic that I have removed from the fault signature matrix does not play a huge role. I have another one where the pump is isolated. Pump number 1, where you can see there's only 1. The other one is below. So we have 1, 2, 3, 4, 5, 6. The 2 faults at the outflow tank number 3 and tank number 4 has not been included. So reasonably nice. And why it's going down sometimes is in my calculation. If some of the vectors are too small, then I just skip it and say equal to 0. So therefore you will see some jumps. That was pump number 1, then pump number 2. Again, also a clear isolation of what's going on here. So quite easy to see. Then, just for a illustration, I have also included measurement noise in some of them to see here how it actually look like. Not necessarily so nice, but we actually get And isolation, it's quite clear we are still valve number 2, that is the faulty one. And it can be done much better. It's not much measurement noise I have included here, but I have designed a receded generator just without any optimization, just design it. I have not included any filters, and of course you will include some cues among some other things to make a more precise isolation of it when you have disturbance coming into the system. So, but it's actually possible. I thought it has been worse, but no. So what we have done, applied the double receded generator for fault isolation in MIMO system. It's again a generalization of the setup for active fault diagnosis, where we now can include both detection signal and reference signals. Whatever we have coming into the system, it can be generated to one input signal directly. Use the scalar vector product for the isolation. Just look at the cosine function, and of course showing on the 4-tank system. Stochastic test method will be the next that will need to be incorporated. Uncertainty also need to be incorporated. It can also be generalized to the case where we have more than one fault. Then the approximation of fault signature matrix will not be exact. It will be an approximation, but there are still something that is very close to the real value of it. So yeah, I think that was more or less this. Time is more or less gone also, so thank you very much.
Someone had a question?
Good afternoon, Professor Niemann. Thank you for the presentation. I have one question about the S matrix. S matrix is used to represent the fault in the system.
Yeah.
My question is this S matrix the same as the dual Euler parameter?
It is precisely the same, yes. Yes.
And then the S matrix is decomposed into two parts, the theta P and SP.
Yeah.
As you mentioned, the SP matrix is assumed to be known. So my question would be, how can we find this SP matrix?
You write up the
yes.
Yeah, just you write up the this system here where you have your parametric fault explicit describer and an LFT description. Then you are quite easy to write up the S function based on this. So, but you need to have an explicit description of your parametric fault in the system. Then it's quite easy to get the next step.
Yes, and I can say in your experimental study you have assumed there is some given SP matrix, right?
Yeah.
Okay, yeah, that's all my question. Thank you for your answers.
So, I don't know, someone else?
Time is gone, more or less.
Short question? Okay. Thank you very much. We thank the speaker. Okay, next speaker. Huh?
No, I'm not next speaker, but if they want to use it. If they want to use it, if you want to use it.
I don't know if we have, because it's written that we use, we have to use that, the material, yes. I don't know why. So our next speaker is, so your name is? Jin Gao. Yes. So the paper is called The Distributed Data-Driven Fault Detection for Industrial Interconnected System with Unknown Topology Structure. So you... This one? No, this one is not one. So you put here, yes.
So good afternoon, everyone. My name is Jing Gao, and I come from University of Science and Technology, Beijing. Today I'm honored to present our team's latest research on distributed data-driven fault detection for industrial interconnected systems with unknown topology structure. I will elaborate on the following four aspects. Today, spurred by the ever-growing requirements for diverse and high-quality products, modern industrial production processes have been designed more and more complex, where many control loops and subsystems are physically interconnected and distributed. It is well known that for such industrial interconnected systems, a fault may occur in one or more subsystems, and the effect of the force may spread to the entire system due to the interconnected nature among the subsystems. Therefore, which will result in performance degradation, even in stability of the entire interconnected system. Associated with the increasing needs for system safety and process reliability, fault detection for interconnected systems has gained significant interest from both academic and industrial application areas. In the literature, a possible approach is regard the entire interconnected system as a new system of high order, to which the existing centralized fault detection methods can be developed and applied. As it shown in the figure, the centralized fault detection methods result in a central computing unit, where the global state input-output information is required. However, in practice, it may be impossible to collect and transfer all the local information to the central computing unit. On the other hand, as the order of the interconnected system becomes larger and larger, the centralized fault detection methods is difficult to provide solutions in a reasonable time. And this leads to another drawback for the centralized fault detection methods for the application. Now, during the past few years, a surge in the decentralized and distributed fault detection methods has been stimulated. And the decentralized fault detection structure design is simple and easy to be implemented, since it doesn't need the information exchange between the subsystems, but it imposes strong constraints on the coupling characteristics among the subsystems. The distributed fault detection structure can fully utilize the information exchange among the subsystems, but thus resulting in higher fault detection performance, but its communication and computation cost is relatively higher than the decentralized fault detection structure. Considering that in the real industrial control systems, the computation and communication ability is limited. Therefore, how to improve the fault detection performance while reducing the communication and computation burden of the fault detection methods is important. As we all know, the connection pattern among the subsystems is varying. So, therefore, the interconnected system exhibit that diverse topology structure. If the information from the connected subsystem is utilized in the monitoring process of a subsystem disregarding the disconnected subsystem. Therefore, the fault detection performance can be ensured with a low communication and computation cost. However, the predominant focus of current distributed fault detection methods are dedicated to interconnected systems with known topology structure, which generally don't take into account the interconnected systems with unknown topology structure. This motivates the primary aim of this work, in which a topology reconstruction method is developed based on the subspace identification methods towards distributed fault detection methods. To this end, let's consider an interconnected system composed by many subsystems. The state space representation of each subsystem is characterized by the first equation, and the lifted state space representation of the interconnected system can be described as the second equation, where AII, BII, AIJ, CII, DI, and ABCD are the system matrices of the subsystem and the interconnected system, respectively. By restitution of the second equation, we can obtain the equivalent I/O input-output model and the input-output dataset model. In order to estimate the unknown state value and reduce the effect of the noises, a common filter-based state observer is introduced. By restituting the estimate state x hat into the input-output dataset model, use this equation. This is the centralized I/O input-output dataset model in the subspace identification method. Next, considering the relevant partition of the centralized input-output dataset model, the distributed input-output dataset models can be interpreted, where the Li and LUI are the subspace matrices of the distributed input-output dataset model to be identified. It is clear that the subspace matrix can be solved by the least square problem, where we employ a LQ decomposition technique to determine the subspace matrix. Next, in line with the identified cyberspace matrix, the data-driven realization of GAMP metric is developed for the measuring the coupling degree among the subsystems. It is worth noting that the data-driven realization of stable image representation is ensure the accurate computation of the GAMP metric and the reconstruction of the interaction pattern among the subsystems. Finally, based on the reconstructed topology structure, the residual generators for the subsystems is constructed, and based on the T-fun test statistic and the designed threshold, the fault detection logic is designed for distributed fault detection. To validate the performance and effectiveness of the proposed methods, a case study is carried on a chemical process. It is evident that the proposed distributed fault detection method can promise the same fault detection performance and the centralized fault detection method. Furthermore, it is clear that the distributed fault detection method reduces the computational complexity compared to the centralized fault detection method. In this work, we propose a distributed data-driven fault detection method for the interconnected system with unknown topology and structure. The main contribution is that a topology reconstruction method is developed based on data-driven realization of the GAMP metric. The subspace identification method for the interconnected system with unknown topology structure is developed. On this basis, a distributed data-driven fault detection method is proposed. In future, we will continue to develop distributed fault detection methods tailored for nonlinear interconnected systems based on neural networks and cyberspace identification methods. Here are some important references that are the foundation of this work. Thanks for your attention.
Someone have a question? Remarks? So, just a comment. So you are interested in interconnected system where the topology is not a priori known, right? The topology is not known.
Yes.
But in the approach, you learn the topology. So the topology is learned and then use it for estimation of the faults.
No.
No?
This work is tailored for fault detection, not for fault estimation and fault isolation.
Okay. And the assumptions about the interconnections, the system is affected by the neighbor system.
Yes.
But there are not exchange of data. There are not communication between systems, right? Only a system affected by the neighbors in the model. Yeah. Yes, this one. So this is Phi and AIG are the interconnection, right?
Yes.
But no system know what the neighbor do, right?
And this work is a data-driven method. So the local subsystem is unknown the state of the neighbor server
okay.
system. Only the needed input-output information is transmitted over the server system.
Okay, thank you very much.
Thank you.
Last remark or comment? Or we thank again the speaker. So next talk, even a little bit early. So is you, your name is Ivo Punchukar. So you will present the active fault detection based on tensor train decomposition. Okay, thank you very much. So I don't know. In fact, I read that say that is use the mouse to point, not laser pointers, not your. So I respect the okay.
So good afternoon, everybody. My name is Ivo Punchukar, and this work was done in collaboration with a colleague of mine, Ondřej Straka and Petr Kichavský. I and Ondřej Straka, we are with the University of West Bohemia in Plzeň, in the Czech Republic, and colleague of ours, Petr Kichavský, is with the Institute of Information Theory and Automation in Prague, in the Czech Republic. So this paper is more on a theoretical side, so please bear with me. Okay. So here is the outline of my presentation, and I'll skip directly to the introduction. So first, I would like to explain you what I mean by active fault detection. Here we have a simple block diagram, and the main idea of active fault detection is as follows. We have a system, and we would like to design something which we call active fault detector. And the aim is to use data observed on the system to generate decisions about faults in the system. However, besides those decisions, we would also like that the active fault detector generates an input signal that is fed into the system, and the only aim of this excitation signal is to improve the quality of decisions. So this idea can be found also in system identification or optimal experimental designs. I mean this idea of using excitation signal. And this problem can be formulated either in stochastic or deterministic framework. And in this paper, I'm going to talk about the stochastic formulation, where in most cases it is formulated also in multiple model framework. It means that we have one model that represents the fault-free behavior of the system, and then we have several other models, and each of them represents one particular faulty behavior of the system. So now what are the goals of this particular paper? I try to explain you the motivation in 2 lines. So when this problem of active fault diagnosis is formulated in stochastic framework, it can be seen as some kind of dynamical functional optimization problem, and then it boils down to solving something which is called functional equation, which is seen here, and the aim is to find a function v that is on both sides of this equation, and once this function is found, we have the solution, and we can design this active fault detector. And the issue here is that it is hard to use a general function v. So one approach to this problem is to discretize the space of psi, and then we can represent this function only over this discrete grid point, with this discrete grid. However, when the dimension of psi is large, I mean like if it is greater than 7 or something like that, then the number of grid points is so huge that it is infeasible to solve. So in this paper, we try to use something which is called low-rank tensor chain decomposition, which is able to approximate the function V over a discrete grid. And we also need to perform some grid design which respects the constraints on the Xi, and these constraints will be seen later on in the presentation. Now I would like to switch to the problem formulation. So we assume that the system can be described by the state space model over an infinite time horizon, where the state of the system is denoted here as k, and it consists of two parts, continuous valued part xk and discrete valued part mu k, and mu k is simply an index into set of the models, so it tells us which model is valid at time step k, and then we have input uk and output of the system yk. And we are assuming that the transition from one state to another is described by the given probability density functions, and we have also probability density function for the measurement. So the aim is to design the active detector that has the following internal structure. It consists of a decision generator denoted here by a function sigma k, and an input signal generator denoted here as gamma k, and both of those blocks uses all available information at time step k, which is denoted here by zk, so it includes all past measurements or outputs and inputs to the system. And the aim is to design sequences of those functions over the infinite time horizon such that the following additive discounted criterion is minimized. Since we are working in the stochastic framework, E here means mean value operator, and L is so-called detection cost function, which measures the difference between mu and decision dk. And here we have a simple example of such a function. If the decision is correct, then the cost is 0, otherwise the cost is 1. And finally, we have some discount factor, which is a number between 0 and 1. So now I would like to talk about the active fault detector design, and here is a short overview of main design steps. The first step is to perform a reformulation of the original problem into new formulation, which is called the perfect state information problem. And it is done using a state estimator. Then we get this new formulation, and it is some kind of standard formulation in the area of optimal stochastic control. So we can write almost directly a theoretical solution to this perfect state information problem in terms of the functional equation I have shown you before in the motivation. However, as I said, it is not possible to solve this equation analytically, so we need some kind of numerical solution, and here we used a so-called value iteration algorithm, and in this algorithm the function V is approximated using the approach where the state space of the information state is quantized, and we use low-rank tensor approximation. So now I would like to talk about those design steps. The first one is reformulation, and it is best explained in this block diagram, where we have the original active fault detector, and now we insert into it a state estimator. Ideally, we would like to have an optimal one, which would provide us with the conditional probability density function of the whole state, Sk, conditioned on all available information Zk. However, it is usually not possible to design such optimal one, so we are stuck with some approximation, some approximate state estimator, and it provides us with statistics. Here I'm going to call them information state psi k. And now when we do this, then the decision generator and input generator are given by single functions. There are no anymore time varying. So we just need to design two functions, sigma bar and gamma bar. And to design them, we treat our original system and estimator as a single block. So we reformulate the problem and look at these two systems as an encapsulated entity. So after the reformulation, we have a new problem where the state equation looks like this. The state is the information state xik. The function phi is a composition of original state, original system, and the approximate state estimator. And now yk plus 1 can be seen as stochastic disturbance because at time step k we don't know the future output of the system. And we would like to design those two functions, sigma bar and gamma bar, such that the following design criterion is minimized, where the function L here is replaced by function L bar, which is obtained during the reformulation as well from the original function L. So now it is possible almost immediately to write the optimal solution in terms of functional equation. So the aim is to find a function v that solves this functional equation, and here all the variables are stripped of the time subscript k because we are working on the infinite horizon and particular time step doesn't matter. Once the function v is found, we can write the optimal active fault detector in the following way. So the optimal decision is given as an argument that minimizes conditional mean value of the current cost, and optimal input, this excitation input, is given as an argument that minimizes the conditional mean value of the future cost, which are encoded in this function v. So now I would like to talk about the numerical solutions to this functional equation, and the approach is, the main idea is quite simple. You turn this equation into a recursive one by adding the iterative index to the function v on the right hand side and iterative index y plus 1, I plus 1 on the left hand side. So we obtain the following recursive equation, and you start with arbitrary function v0, plug it into the right hand side, and you obtain function v1, and you repeat this process until the function vi stops to changing. So it's similar to the approach that is used, for example, Gauss-Seidel method for solving a system of linear equations. So now we have this recursive equation. However, we need to somehow represent the function vi at each iteration, and the approach we chosen is to perform the quantization of the space of xi. Here is a simple example of two-dimensional space, and these dots represents the grid points that are selected. The function v is computed only at those points, and if we need the value of the function at some not grid point, we perform some interpolation. And as I said, when the dimension of xi is larger, then the number of grid points is so huge that it is infeasible. So in this work, we use so-called low-rank tensor train approximation to represent the function vi. So now I would like to explain what I mean by tensor, because in mathematics it has some specific meaning, but here it's a simply d-dimensional function where the domain of this function is discrete, and it is given as a Cartesian product of these simple sets. Ij set is a set of integers from 1 to nj, and another view of this tensor is just a d-dimensional array of function values. So number of elements is given by the following expression, and this number can be quite huge if the dimension is even not so high. So there are several tensor decompositions, and one of them is called tensor train decomposition, and it assumes that this function over a discrete set can be written in this specific form, where we have a sum of these products, where Fj denotes a smaller tensor, in this case three-dimensional tensor, and the important thing here are the ranks denoted as Rj, and they can be seen as the upper limits of these sums, and the number of elements in those smaller three-dimensional tensors is given by this expression NTTD. So if the ranks are small, then the number of elements is manageable compared to the number of elements in the full tensor. And for any function f or tensor f, you can find this tensor train decomposition, I mean like exact decomposition. However, you might need large values of the ranks, and we don't want that. So it is possible to find some low-rank tensor approximations, and for a given tensor f, let's say that we can, for example, try to find a best low-rank approximation in a way that we have a given tensor f, and we would like to find f hat, such that this Frobenius norm is minimized, subject to the condition that the ranks are smaller than some selected values, or we can try to minimize the maximum rank, subject to that this Frobenius norm of f and f hat is smaller than some prescribed precision. So both of these problems are not trivial. However, there are algorithms that solve them approximately. They go under the name usually TT cross, and there are some extension of the skeleton decomposition of a matrix. And they evaluate the tensor only along selected fibers, where fiber means that you fix all the indices except one, and you evaluate this tensor just along this one index. And these algorithms are implemented in several toolboxes. We use the TT toolbox that is for MATLAB. So, and last issue that we had is that originally, as I said, there is the tensor is defined over a Cartesian product, and it is hard to cover our desired space with such a grid, because, for example, when we use so-called generalized pseudo-Bayesian estimator, then it provides us with the following statistics. There are stacked into this information vector psi k, and there are some conditional mean values of the state xk for each model, some conditional covariance matrices for each model, and also probabilities here denoted as pi of these individual models. So, for example, for covariance matrices, they have to be positive semi-definite, or for the probability vector, some conditions also has to be satisfied. So we address this problem by using some nonlinear transformation, and it is depicted in this figure. So on the left figure, we have a grid for the indices of the tensor. So the indices are integer numbers. And in the middle, we have a grid for some intermediate grid of the parameter. So the indices are not anymore integers, but some real numbers. And the transformation between those two grids, denoted as H1, is linear. And then we have on the right-hand side, we have the final destination space. Here is the example for the probability vector. Let's say that we have 3 models. Then pi1 is the conditional probability of the first model, pi2 is conditional probability of the second model, and pi3 can be computed as 1 minus sum of those two. And all available points are in this triangle. You can see it quite clearly. So we need some nonlinear transformation H2 that transforms this hypercube into this triangle. And similar transformation is needed for the covariance matrix to keep it to be positive semi-definite. I'm not going to give here the details of these transformations, and I will skip to the numerical example. So in this paper, we used only a simple model where we assume a linear second-order Gaussian model where part of the state xk is directly measurable, and there are only two models, the fault-free model and faulty model. And the only important thing I should mention is that the matrices of the models are selected such that the steady-state gain from input to output is the same for the models, for both models. However, the time constants are different. So it means that if the input signal is constant, then it is bad for the quality of detection. And when the active fault detector is trained offline, and then we use it for online detection, then it can be seen that the generated input is almost a square signal. In the middle, you have the xk, which is the continuous part of the state, and in the bottom figure, you have the true mode mu k, which is denoted by blue dots, and decisions denoted by red circles. And it can be maybe, I hope, seen that, let's say at the beginning, there is a model 1 valid, then it switches to the model 2, and you can see that the decisions follow, for example, after 3 or 4 steps. So the quality of the decision is quite good in this example. So I would like to conclude my presentation. First, we designed an active fault detector using a tensor train decomposition that was used to represent the function B. Then we also performed some nonlinear transformation between tensor domain and information state space domain. And I would like to point out that this approach was also successfully used for more complicated numerical examples than is presented here in this paper. So thank you for your attention.
Someone have a question? Remark?
Thank you for your presentation. Actually, I'm not sure I understand you. You might mention it, so you need to solve an optimization problem with a rank constraint, which a given upper bound of the rank, right? I mean, you solve the problem with yes, this one with the rank constraint. So the Rj max is the upper bound of the rank.
Excuse me?
I mean here.
Yeah, the ranks are.
Yeah, the rank, the upper bound. So the maximum.
The upper bounds are selected by user.
Okay,
so if he doesn't know anything, he can choose them in a wrong way.
So what is the? Do you have to how big is the number? Can you select to? Do you have a range?
Well, it depends on an example.
Okay.
In some example, let's say that the rank can be, let's say, 14, and for another example, when the function is more complicated, the ranks can be higher. Usually, we use the second formulation, the second optimization problem, because we need to ensure that the quality of the approximation is satisfied in some sense, so that the distance between the function tensor f and the f hat is smaller than some prescribed epsilon.
Okay. So if I understand correctly, you need to have some insight of the system.
Yeah.
Okay.
Yeah.
So
and this optimization problem is so similar to the case of.
Okay. Thank you. We can discuss later.
So next speaker. So next speaker is Gustavo.
Yes.
Gustavo Baena. Unife modeling of dead zone, dead band hysteresis, and other faulty local behaviors of actuators and sensors.
Oh, is it to put full screen?
Control L.
Control L. Ah, okay, perfect. Okay. Hello. So, welcome everyone. My name is Gustave Beignet. It's a joint work with Jean-Christophe Ponsard and Benoît Marx. And my title is a bit long, so I will say the short version of this. It's about dead zones. Okay, I will be a little bit more generic than dead zones, but I will propose a representation that in particular allows to treat dead zones. So this is plan of my talk. So just to say it quickly, first there will be like more theoretical part and after application. So not very complicated. So this slide, it's provocation. I think you all know what dynamical system is. It has input on one side and output on the other side. What I want to insist on is, you see, it's basically the opposite of what mathematicians will do. Mathematicians, they will typically have arrows between objects, and arrows represent a morphism. But here, the system which could represent what we could call an application in mathematics, it's actually the box, and the signals, they are the arrows. So it's kind of opposite of what mathematicians do. But I will come back to that later. So actually, of course, it's a little bit more complicated because for a system, you need something to give you an input, and the system has to have something that gives you output. And typically, we call them actuators and sensors. And it is well known that they are subject to some local nonlinearities, and dead zone is one of these local nonlinearities. So you want to give some kind of input, but in reality, it's another input that is actually fed to your system. And it can happen locally. And when it happens locally, then we have some description, some dedicated model for these local nonlinearities. So this is the most well-known one. It's the dead zone model. So you will have, for a whole range of input that you want to give, it will just give you 0. And outside you will have, of course, some slope that is not usual. And this is typically what you have with dead zones. Sometimes they are called dead bands, and it seems like that in the literature it's more or less synonyms. I will introduce a small difference. I will call dead bands. Some people call this dead zone as well, but you see the difference between this dead zone and this dead zone that I will call dead band is here you have a complete loss of information. There is some input that you cannot reach. Of course, the jump is not really instantaneous, but with this model, since you assume that it's instantaneous, there is some input that you cannot give to your system. Okay, and another well-known local nonlinearity that you probably have heard of as well is called the hysteresis effect, and this time the derivatives of the input plays important role as well, because depending if you go from left to right or from right to left, in the end, the input that you will give, that you will feed to your system, will not necessarily be the same. And these kind of local nonlinearities are discussed a lot for actuators. They can also happen in sensors, and it is a little bit less discussed in the literature. We will see why. So first, let's talk again about actuators and dead zone on actuators. It is well studied by the literature, and there's a good reason why. It's because there is a mathematical solution when you're dealing with actuators that is very straightforward. So again, we do opposite as mathematicians. Mathematicians, when they see this dead zone, they see that the function is surjective, and they will see that the function is right invertible, because they see equation from right to left. You apply a function to an element. Here in system theory, we do opposite. We have our signal on the left, and we apply a filter to it, and so we read from left to right. And because of that, you see that if you put a dead zone inverse on the left of the dead zone, you can actually compensate for the dead zone of the actuator. So because the dead zone is right invertible, you can actually compensate it on the left. It's opposite between system theorists and mathematicians. So here, in theory, you have perfect inverse. So yeah, of course, this leads to a lot of development. But you see that this inverse, it has this instantaneous jump, and you have to know your model of dead zone perfectly. So in practice, you will have some local uncertainty, for example, because you don't have this instantaneous jump. And because of that, this leads to some noise at the place of the dead zone. So there is some solution in the literature that will typically assume that indeed you have a slope here, that the slope is maybe not perfect, that you don't know exactly where your dead zone begins and ends, and they will assume some incertitude on that, some uncertainty, sorry. Me, I will assume uncertainty in a much more straightforward manner. I will say, like, if you are between -1 and 1, then you know that your actual output is between -1 and 1. So it's kind of a local it's a local differential inclusion. It's a differential inclusion that is only valid for a specific range of values. Whereas differential inclusions that are typically treated in the literature, they are on the whole state space. Here it's just for some values. So you can see it as local noise as well. It's kind of noise, but only applies for this range of values. And I will talk now about sensors. Sensors, dead zones on sensors are less talked about in the literature. And you will see why. Because again, this dead zone function, it's right invertible, which means in system theory, you cannot put a filter on the right to inverse it. You must put it on the left. But you cannot do it for a sensor, because sensor is what gives you the output. So because of that, you have to, if you want to put a dead zone inverse after a sensor, you can do it. But then, when you are on this range of value for y, then you don't know what to apply here. So again, this leads, there's an unavoidable loss of information, and this leads to the same uncertainty box. So it's the same as the previous one. And actually, a lot of local uncertainty, you can fit them in this very simple model that is differential inclusion, and you can fit the hysteresis model inside, you can fit the dead zone model inside, the dead zone potentially with already an inverse applied to it. You can fit the deadband as well, it will fit the loss of information. So yeah, this model is very generic. So of course, this is my proposition. I come back to a mathematical framework. When you see this through mathematical lens, you want maybe to see the symmetry of the system. And what happens if you reverse the arrow? If you come, I don't know, from category theory and so on, reversing the arrow means taking the dual. So you have a notion of duality that appears naturally with this representation. Because in both cases, you have a symmetry, you have a loss of information. So I say that this representation is good because, one, it's generic. Two, you have this new notion of duality that is not discussed so far as I'm aware in the literature. But of course, since you don't know exactly what kind of uncertainty you are dealing with, you don't have a model for the dead zone, you just have a loss of information, you are more conservative than usual approach. But if you don't know exactly, like there's a specific range of values where your actuator gives you something weird or your sensor gives you something weird, yeah, you could maybe use this representation and obtain at least some partial results. And I want to insist a little bit on this notion of duality as well, because there is one duality that is talked a lot in system theory, it's duality between controllers and observers. So do you find it with this representation? Taking a linear system, if you want to design an observer or if you want to design a state feedback controller, will you have the same notion of duality when you will have this problem at the sensor level or at the actuator's level? And it turns out close. So this is typically your internal dynamic, and here you have state feedback control. But here you have this local uncertainty. And here you can establish easily ultimate bound on the X that you want to reach, the state that you want to reach. Can you do it as well for observer? And you will see here there's a nice symmetry between the two situations. It's the same, you just revert the arrow once again. So of course it's dual, but it's not quite the same, because if you want it to be perfectly dual, you would need here to have the estimation error. And there, what I need to represent is actually the state and the estimated state. Why? Because in fact, the sensors, they will give you an output that is uncertain because of this local uncertainty. But when you design the observer, you kind of design a false actuator that applies to a false sensor that gives you the output of the system, the estimated output. But you could apply nonlinearities to it as well, but the problem is that the nonlinearity will not be applied to the error, it will be applied only to the output of the system itself. So you have a strong analogy, but it's not complete duality between observers and state feedback. But otherwise, in this representation, if you just focus on actuator and sensors, you have this duality. But you kind of lose it a little bit for state feedback and observers. So now I will go a little bit into the technical results. Maybe I was a little bit fast, so I will maybe spend a little bit more time. Theoretical results, so this one is very, very, very straightforward. So you have your linear system, and you have your actuator that is here. You want to apply a U, but instead you apply U tilde, because you have this local nonlinearity that you can translate to U, so the identity, plus a noise, but this noise will only be applied when you are between -1 and 1. And when you do that, then, okay, you design a state feedback, you do it through the regular LMI. Here I wrote a BMI, but of course you multiply left and right by P-1, and you end up with the regular LMI. And here I impose a decay rate alpha, because it shows up in the expression after. And actually, if you just impose this, so maximum decay rate, minimum decay rate to the system, you can find that in the end your system will be ultimately bounded by a quantity that depends on how much noise you inject locally on your dead zone, on this representation of the dead zone that I suggest, which is not, like, it includes dead zone, but not only. And this is the radius of the ultimate bound. This is a P matrix of the ellipse that defines this ultimate bound. And if you want, I can go a little bit in the detail of the proof. What is interesting to notice is that if you impose a big decay rate to your system, because you will pass very fast on this local uncertainty, it will affect you less. And because of that, you see that the radius of the ultimate bound is actually inversely proportional to the decay rate. Okay, so this is very easy ultimate bound, and if you see the proof, you will see that it fits in one slide, so it's not very technical. You have the usual Lyapunov function, quadratic Lyapunov function, because we are a linear system. And of course, you have here, this you can replace by the minimum decay rate that you impose. And here you have the noise that you apply that plays a role of affine term. And this affine term, you can actually factorize by x in the next step, and you will see that your Lyapunov function, the derivative will be strictly negative only if x is superior to this quantity that will give you a circle outside of which your trajectory will be decreasing, and then you find the level set that encapsulates this circle, and you end up with your ultimate bound. So maybe I was a little bit fast, but this is very usual, and this will work also if this delta is not only local, but is applied to the entire actuator. So this is actually very conservative result. And in the paper, if you want, I detail in other theorems way to handle the fact that this delta is only local, so this noise only applies to a certain range of input values. So application, so I take this very simple linear system, and here I invented some stupid local nonlinearity. I don't think this ever happens in practice. I took something that is very stupid. So for U that is between -1 and 1, you will actually apply this thing. It's not important what it is. It's just like very big formula, very ugly nonlinearity. And you take state feedback to impose a decay rate of 2. For Lyapunov function, I took very basic one as well. I just took circle. And so this is the input that you will have. In blue, it's perfect case where you don't have local nonlinearity. And in orange and, it's orange and yellow, you actually have two ways of applying these local nonlinearities if you want to distinguish, because there is several ways to apply local nonlinearities to a linear system. If you want to go a little bit into details, there's a paper for that. And here you have the states, and of course, you stabilize somewhere with the nominal behavior, but of course, when you have local nonlinearity, you see that you stabilize somewhere else that will be in this ultimate bounds. And the ultimate bound I just discussed a few slides before, it's a big red circle, so you see that is quite conservative, but actually in the paper I found less conservative ways to obtain ultimate bound. And yes, you can actually find this green one using a Lambert function that is a bit technical, and the blue one, you can obtain it using polytops. So, yeah, to conclude, yes, I present a generic representation of local nonlinearities that you can have on actuators and sensors, and you find this representation to be quite generic. It actually introduces a notion of duality that works for the actuator and the sensor, and you kind of find it as well for controller and observers. But of course, this representation, it's quite conservative because we assume in any case that there is a complete loss of information. So thank you for your attention, and if you have any question, thank you.
Thank you. Someone have a question? Remark?
Thank you very much. Very interesting presentation, and I really like that it's very generic, the model. I was thinking that if you, for example, go to the slide where you have the representation of the square in the middle, it can be, that one. It can be very typical, for example, that you could approximate this roughly with a limit cycle. So you can consider a first-order system that has some sort of limit cycle dynamics, maybe skew a little bit to make it look like more like square.
Yes.
But then, if you do that, you will have an explicit or forced, let's say, behavior of the system in the dead zone, where most of the case in control design, you wouldn't want to go there. Very nonlinear friction and so on. So how an approach like that, for control purposes, for using it in control design, could compare to something which is a bit more conservative, like the one you present?
I don't know. I was thinking to maybe use an estimate of the error that you actually have between what you really apply and what you want to apply, and maybe use it in real time. I don't have a definite answer for this. And this paper is only introduction. And the problem with this approach where you compare what you actually apply to what you want to apply is that it will only work for actuators. So I think there's a direction to go there. I think some people use it already for dead zones. This is how they will fix the fact that the dead zone is a little bit uncertain. But precisely for this representation, for now it's open question. So I don't know.
Thank you. Time for our last question. Yes. Are you interested in computing invariant sets instead of ultimate bounds?
The ultimate bound is itself an invariant set.
Conceptually, it's not the same.
It's
like the final set you achieve, but it's not invariant because you can go out in terms of. It's not the definition of invariant set.
Invariant set is like your Lyapunov function. It will.
If you start inside, you remain inside.
Yes.
And ultimate bound is if you start outside, you converge to inside.
Yeah, but once you are inside, you don't go out anymore. So in a way, it's invariant. I agree, it's more generic because you reach this final state, but you stay inside.
Yeah.
So it's invariant.
Yes.
It must be invariant.
I remember that the conceptually is quite different because ultimate bound could be you can go out in infinite time, and in the infinite time you go inside.
Asymptotically.
Yeah.
Okay.
Yes. You can go something like that.
Yes.
Before go inside.
Okay.
So it's not guaranteed that.
Yeah. Okay. I see.
You are always inside at all times.
Okay. Okay. Here
it's a positive variance set. They say that at all times you are inside.
Yes. Yeah. Okay. So here we are in a case where it's the same. Because
probably.
Yeah. Because the Lyapunov function is strictly decreasing, like it will not.
It's strictly decreasing, and this case is the same.
Yeah.
Okay. Thank you very much. Okay. So we come in for the last. So the last speaker is in the virtual, it seems. Okay.
I'll try to find it.
So it's an interval observer design for fault diagnosis. Probably presented by Alexei Shirach-Bok.
No sound. No sound.
Is someone disconnected? It seems it's virtual, but then someone has to.
I don't know where the sound is.
Someone is connected by internet to present that paper? Here say that it's virtual, so
I can hear it here, but
you can hear someone?
yeah.
Ah, yes?
But I don't know where.
How we can open this the voice? Someone has to. If you put, try again. Yes, and we just play the presentation, no?
Yeah.
You run the presentation.
Yeah. Just start.
But this, we listen so.
To what?
The sound is very small. So, probably the volume. The volume. Yeah, yes. Audio is in the presentation, it seems. I don't know.
The external disturbances by determining upper and lower bounds of the system states. Besides, the interval observers are used to solve the problem of full diagnosis. In many existence papers, the observers is designed based on the original system that results in complex methods to minimize the influence of the disturbances on the process of food diagnosis. The main contribution of this paper is the interval observers are designed to solve the problem of food diagnosis for dynamic systems described by linear models under the disturbances. To decrease the number of erroneous diagnostic decisions, the observers are designed to be insensitive or having limited sensitivity to the disturbances. Unlike the known papers, the designed observers are based on the reduced order model of the original system that allows to reduce the interval width. Besides, this allows to use the canonical form of the observer that simplifies the procedure to design the interval observer. The main models. The system is described by the following linear models. Rho T is a bounded disturbances. The function Vt describes the folds. They are considered as a consequence of inadmissible changes of the system parameters. It is assumed that in the case when this inequality holds, is not considered as a fold. The following case for some P0 is qualified as a fold, which must be detected. This relation is understood element-wise. Solution of the problem is based on the reduced order model of the original system of minimal dimension, generally described by the following equations. For matrices F star and H star are presented in the following canonical form. Note that unlike the observer, the model is the equal object. In fact, it is a part of the original system. The matrices describing the model, which is insensitive to the disturbances, can be found from the following equation. Is these matrices. This equation has a solution if the following inequality is true. If this condition is met, one starting from k equal to 1 determines the minimum k, then finds a solution of the equation. Finally, one calculates the matrices describing the model. As a result, the model has been designed. Interval observer design. The interval observer is based on the above model and is given by these equations. This is the following notations for arbitrary matrix A. The following theorem is true. If this inequality is true and the faults are absent, then zero belongs to this interval for all t. Measurement noise. Measurement noise can be taken into account as follows. The general description of the interval observer is transformed. The measurement noise are taken into account by the additional terms in these equations. The other equations remain. Clearly, the interval width increases. A robust solution. If the model insensitive to the disturbances does not exist, one has to use the robust solution, minimizing contribution of the disturbances in the model. In this case, one finds for some k all linearly independent solutions of the following equation and collect them into this matrix. Then one finds single value decomposition of this matrix. The first transport column of the matrix UN is used as a vector of this coefficients. Finally, one calculates the following matrix. Fault isolation. To solve the problem of fault isolation, one has to design a bank of interval observers. Every observer in this bank is sensitive to some group of the faults and insensitive to others. This suggests the following procedure. Design the model insensitive to the first fault and find the matrices describing the first model. As a result, the first interval observer has been designed. The first model is sensitive to some faults. We choose among them the first fault and design their energy. The second model as the observer is sensitive to this fault. The process is being continued analogously so long as all faults are considered. Example. Consider the discrete time model of the electric Sironian actuator described by the following equations. X1 is the output rotation angle and the reducer output shape. X2 is the output rotation velocity. X3 is the current through the Sironian actuator windings. The model insensitive to the disturbances is given by the following equation. The interval observer is described as follows. For simulation, consider the system with the following values of parameters and control. The admissible interval for dt is as follows. Simulation results are shown below. In this figure, you can see the faults, the case when the faults are absent. You can see that 0 is between this interval. In this figure, you can see the case when the faults has occurred. Fault has occurred. In this case, 0 is out of interval. Thank you for your attention.
We are more or less finished, so question for this presentation, yes, you need to send it to the authors. So it was a video, so I would say thank you very much for your attention for this session here, and thank you very much for your help. And then I think it's a coffee break now, so thank you very much.
Last point, okay.
Okay, so hello and good evening. So it's my pleasure to co-chair the session. So together with my colleague, so Professor Ping Zhang. So for today, the session is about the fault diagnosis in electromechanical systems. Today we have a 5 presentation. And the first presentation is going to address the topic of application of the digital signature to attack detection in a DC motor control system by Barbosa. It's presented by the co-authors. So please, the speaker for the first presentation is in the session.
Yes. I am the presenter of the first talk.
Okay, so please, floor yours, Professor Ping Zhang. Maybe you can use the mic.
Thank you very much. So hello, everybody. Welcome to my talk. So it is about how to apply the digital signature to attack detection, and we apply it to a DC motor system. So at first about the background of cybersecurity of control systems. Nowadays in the industrial plants we have more and more networking between the sensors, actuators, and the controllers. And moreover, the cloud-based control is also a very hot topic nowadays. So the automation suppliers are preparing the solution for that. So in this way, because the use of the different networks, so the plant becomes more flexible and reconfigurable. But on the other side, the risk of cyber attacks also increases a lot. For instance, the attacker may eavesdrop the signals transmitted over the network, and they may even manipulate the signals. So the motivation of this work is namely by the observation that the digital signature has been widely applied in everyday life. We can give digital signatures in emails, and we can sign the contract applications with digital signature. So the question is, could we also use digital signature to improve the security of control systems? If we do that, could it satisfy the high real-time requirement that is required for the control systems? So the focus of this paper is namely to do some preliminary investigation and implement digital signatures and validate the performance with the help of a DC motor experiment platform. So now, at first, some discussion about the digital signature, some simple introduction. So what makes, what are important for digital signature is namely three things. So at first, the message authentication. So that means if the digital signature is used to sign the document, we make sure that, we can be sure that the message is from the correct sender. And second thing is namely integrity. So the main purpose of the digital signature is also to ensure that the content of the message hasn't been modified during the transmission. So what we receive should be the same as the message that has been sent. And third thing, which is important for the digital signature, is the long repudiation. So namely, after a sender has signed his message, and then later he cannot deny that he has ever signed it. So that because he has to sign his document with his private key, and only he knows about this key. So that's why this can be achieved. And for our application, today is important, or the first two properties, the message authentication and the integrity. So now, how does the digital signature work in general? Is that so the sender has some message to be sent away. So that's the message here. And so what he does is that the sender will take his private key and make use of the signature algorithm to generate some signature. So the signature is the output of the algorithm based on the private key and based on the message itself. And let's call the signature S here. Then both the message and the signature will be transmitted over the network to the receiver. Then the receiver will receive the message, the Y prime, and the signature S prime. And the receiver just uses the public key and run the verification algorithm. Then it can tell, so the verification algorithm can tell whether the message is true from the true sender, and whether the message, the content hasn't been manipulated. So that is how it works. And if we look at in general, the digital signature algorithm, so usually it employs the asymptotic cryptography. That means there's some secret key, and the sender will hold the secret key, and there's some public key. So the recipient of the message will use the public key to verify. There are different types of digital signature algorithms. Here are just several typical ones, which are most famous. So first one is the RSA signature algorithm proposed by 3 persons. And second one, Gamma signature algorithm. Third one, digital signature algorithm. So the different digital signature algorithms are different according to the principle why it makes the signature secure. So the RSA signature is secure because it's very hard to factorize a big number into large primes. So it's a very hard problem, and the attacker may need much time to get that solved. And the Gamma signature algorithm makes use of the hard list of discrete logarithms. And the digital signature algorithm is also based on the hard list of discrete algorithms. Specifically, in this talk, we have employed the elliptic curve digital signature algorithm, the ECDSA here. The reason is because the elliptic curve digital signature algorithm just need shorter key. So there's not so many bits in the keys in comparison with other digital signature algorithms. And a shorter key means for us a shorter processing time, less online calculation, less network node. So it is make it easier for us to do the real-time implementation. So in this table, it's just a comparison of the algorithm we have used and the standard RSA algorithm. So we see that to achieve the same security level, the ECDSA needs less bits, so much less bits than the RSA algorithm, just as one example. So now, what does the elliptic curve digital signature does? Is namely, so at first the sender needs to generate the key, and he will keep the private key with himself, and he will send the public key to the recipient, and then he will sign by running some here some mathematics. So note that the multiplication, the addition here are done in the ways required in the elliptical curves. So it's not the standard multiplication indeed. And also there's some mode operation which plays an important role. And later in the verification, so the recipient will take the public key and will take the message he has received and take the signature he has received and check whether they are consistent or not. And if we integrate digital signature in the network control systems, then it looks like this one here. So the sensor will sign. So after the measurements have been got, will sign the message at first, and then both the sensor signals and the signatures will be sent over the network, and then the controller will receive both signature and message, do some validation at first, and use and find out so whether it's the content hasn't been manipulated or not. And the controller calculates the control input, so this message will be signed again, and the control input and its signature are sent over the network. And at the receiver side, so let me the actuator will at first run the verification algorithm to find out so whether the control input signal has been manipulated, has been modified during the transmission, and if it is modified, then some countermeasures will be taken. If not, then he will use it and give this signal, will impose this signal on the plant. So now we validate the digital signature algorithm in the experiment with the DC motor. So here we have the a very standard experiment platform which is available in many labs, and so here it is can be described by a state space model with 3 states, and the digital signature for the implementation we have used some available libraries. We have used the elliptic curves. So this one, so y squared equals to x power 3 plus 7. And so very often in the digital signature, people also integrate it with a hash function, and so that is a hash function we have used. And the main purpose is if the message is long, then we can reduce the length of the message. So now we look at the experimental results in the attack-free case and in the attacked case. In the attack-free case, so everything is running well, and we see that after we have added the sign and the verification process, we see that in the first figure, the blue one is namely the true output, so namely the speed, rotational speed, and the orange one is namely the reference signal. So we see that the DC motor can follow the given reference signal very well. And the control input signal is shown in the figure in the middle, and the tracking error is namely the difference between the reference point and the true speed. So we see that the plant is just running as usual with a little bit, so here it is so both a little bit the influence of the disturbances and also so in this, so here the small deviations, I don't know the exact reason, but it's very small deviations in between, we can see it. And then in the attacked case, so here we have simulated a mine in the middle attack. That means the message during the transmission is modified, and how we have modified it in the experiment is namely the true control input signal calculated by the controller has been replaced by a random value between -5 watt and 5 watt shortly after 12 seconds. And now let's see what the digital signature has found out. So here, because the actuator, so after he has received the message and to the signature, he will run a verification algorithm. So the actuator side, so it was found out because there's an inconsistency now between the signature and the data message content. So it is found out at 12 o'clock 50, so as shown in the figure in the middle here. So this attack was then rapidly detected after one sampling time, and as a countermeasure, so it was programmed in that way, so as if any attack is detected, then the motor should be shut off. So that's what we see in the top figure, that the speed has been dropped to 0. So that is because that is the pre-specified countermeasure to cope with the attack. So now let's look at the computational aspect, because for the calculation of the digital signature, we work with a little bit bigger numbers, not so big as in the encryption, but still it is some big numbers. So the question is how much time it needs to calculate the signature and also to do the verification, carry out the verification algorithm. So here, from the record that the message is sent from the sensors to the controllers on the one side, and it is sent from the controllers to the actuators on the other side. And the overall computation time is, so this two times, so in the last two columns, at so the controller processing time here. And we see that the maximal time, it is about so less than 20 milliseconds, and the sampling time of this DC motor is 50 milliseconds. So the time is enough to do the digital signature. So overall computation time is smaller than the sampling time, and so the approach has the real-time capability. So finally, in conclusion, the digital signatures has been applied in this work to the DC motor control, and the control performance is satisfactory. It's not much influenced by the signature procedure. And in the next step, so as mentioned, it is just a preliminary investigation. What we are going to do in the next step is to think about, so how about MIMO systems, and how about larger systems if we have many signals, so surely we need more time, and how to handle the keys, and also to do some vulnerability analysis for the digital signature based approach, because for instance, digital signature is indeed not secure against the replay attacks. So if the people records the data, including the digital signature, and replay it, then it's not possible.
That's a very hot topic, but in your simulation result, experimental result, I noticed that the DSA time thank you. So this is a very inspiring presentation, but in your experimental result, I noticed that the DSA from the sensor to the control is much closer to the mean value compared to the from control to actuation. So are there any reason that the time from sensor to control is much close to the mean time with respect to the control to the actuators?
No, I don't know. So, but for me, it looks like the time from the sensor for the signature from the sensor output signals and the digital signature procedure for the actuator signal. I don't think that there's very big difference, because if you consider also the variance, so if we consider also there's some variations, so it's not, because we are handling with random numbers, so the calculation time each time could be different. And if we consider also the variance here, you see that for the sensor signal, the variance in this experiment, it is a little bit higher than the variance in the controller side, and I would say that they are almost in similar ranges. It's interesting, so we'll have a closer look. But currently, I don't know the exact reason.
Thank you very much. Any other question from audiences? So if not, let's thank again Professor Ping Zhang. Thank you very much.
Yeah, thanks. So the next speaker is Professor Karimi from the University of Maryland, or Technical University of Maryland, and he will talk about weighted feature fusion of convolutional neural network and graph convolutional neural network for mechanical fault diagnosis under time-varying speeds. So a very challenging problem.
Okay. Thank you very much, Professor Ping Zhang, for the kind introduction. So good evening. So my name is Hamidreza Karimi. So thanks to my PhD students, you and also collaborator, Dr. Liu. So I'm going to address the topic of about the basically related to the fault diagnosis for the rotary machinery. Particularly, we can see that we are looking at some particular failures in the mechanical component. But for today, we have some tools from the deep learning based on the weighted feature fusion, convolutional neural networks, and also the graph convolutional network is a mix of these three techniques. We are looking at the fault diagnosis. But there is one issue about the time varying speed, because this is one challenge in the mechanical application, because the conditions are changing based on the time and also the condition from environment. And that's it, the fault diagnosis for the time varying speed is challenging, and this is the reason that we focus on this particular challenge. So the presentation today, after the short background about the motivation to this kind of the work, I'm coming to introduce the framework of this algorithm for the fault diagnosis. So I will discuss about the data sets, because the fault diagnosis needs the amount of the data for using to evaluate the algorithm, and then the experiment, and finally the conclusion. So motivation for the fault diagnosis, it comes from the rotary machinery, from the cars, from the train, either to the wind turbine. So in most of these complex systems, we have a lot of components under pressure, under loading. And some loading are the dynamic loading, so especially for the wind turbine, for the aircraft engine. But still, there are some components under high pressure. So this presentation focuses on the bearings, and if you look at the bearings, for this component we have several damage or the failure we can expect. So one failure could be inner race or outer race, or even for these ball bearings we can have a ball fault. So now the point is that how to detect or how to predict or how to make a prognosis of any failure it occur on this particular component under varying speed conditions. So for this case, because the bearing has a large contribution to the failure or the downtime and also the maintenance of the mechanical systems, and roughly I could say that at least 40% of all the failures or the damage for the mechanical system it comes from the bearings, and that's it. This is a high motivation for looking at this application. So if you look at this kind of the graph, so the point is that for time varying conditions, so or the speed of the engine or the speed of the rotary machines, so we could expect to get some features from the data. So this data could be acceleration data, and this acceleration data, so we can expect for the healthy and also for other class of the fault in the system. So if you for instance, for this 9 class, if you have an 8 type of the damage or the fault and 1 healthy case, always you are dealing with the 9 different feature signal. And based on this analysis, and of course we always know that the noise is a part of the data. And this is a decision making to make a classification of the basically the data, and this is a topic of the prognosis or the diagnosis in these talks. So for today, so we put on in front of our researchers several algorithms, and including this topic of the graph convolutional networks. So if you look at this learning model based on the input layer, hidden layer, output layer, then you can notice that we have some pattern in the graph model in the input layers. And also we have a graph model in the output layers. Of course, the relation between the input and output can be visualized based on this convolutional basic model you can see in this mathematical equation. And this mathematical equation is driven by the variable, the theta. And this parameter is a spectral graph. And of course, if we know about the graph modeling, so we have a lot of parameters. So all should be considered in the modeling. For instance, we have the eigenvalues, and also we have a Laplacian metric. So the matrix of L is a Laplacian metric, is modeled the graph. And based on this convolutional model we have, and then we are coming to see what kind of output we can visualize. So in the output layer, so based on this GCN network, so we can get this relation between the one could be the predicted and one could be the real case. And now we are looking at how much we can believe to this kind of the output we can capture from these graph networks. So the GCN, it becomes basically more popular because based on this kind of the non-Euclidean data, so based on the distance between your data set, based on your label data and your sample data, so you can do the classification, and this is based on the GCN. So the competitor for us is a CNN model. Convolutional neural networks, of course, it has a high accuracy based on the different layers, convolutional layer, batch normalization, ReLU function, and if you come to some other, basically the pooling layer, and finally you can do the classification. But the difficulty for CNN is the training. So, but the problem is that in the context of the fault diagnosis, the data set is quite limited. And therefore, if you want to train the CNN, you need to have a high number of samples per class. And in many cases, the CNN has a limitation to be realized and to be used for the diagnosis. So the framework we can propose based on the GCN, it means that if you could make as an input layer, so based on the graph model of X, so then this could be normalized, and this normalization based on the graph model, based on these close neighbors of basically the nodes we have in the graph model. So based on this, and you can get the graph in the output. This is a process of the graph generation. And also we have some basically the graph generation. You can see it works based on this kind of the neighbors checking point and to check the distance. And then we are coming to the weighted. So we need to give a weighting to what kind of the basic graph model we can capture it. So this is based on the structure of the CNN and also the GCN. So based on this weighting between the two data you get from GCN and also CNN, we came to the loss function. So the loss function, you can see, is based on the averaging model, based on the, for example, how many labels you have, and also it depends on your true labels, predicted labels, and also based on number of samples, and also to decide about the sample I depends on which class in your clustering model you have. So this loss function basically should be validated, and also we should look at the convergence, and this is a part of the framework we have. So let's back again to our data set. So this data set you can see for this machine. So basically we try to look at as I mentioned before, that the fault on the inner race, outer race. But we are labelizing a data based on the severity of the damage on the bearing. So you can see we have a mild, a moderate, and the severe case. And also the frequency of the sampling time you can notice on this slide. And for this machine, we have a healthy case, and also we have some other non-healthy case. At least we have 5 class of the non-healthy case and 1 healthy case. So based on this data set we have, we need to see how to train the model. So the training based on some existing result, we try to look at the 3 different data set. For example, the data set, the proportion 80%. So proportion is very important because one of the reasons is that if you are using the CNN, the proportion should be high in terms of to get the high accuracy. And that's it. If you come from 80% to 60%, even to 40% with a very low proportion, we need to see about the robustness or the resilience of your diagnostics respect to the less data. So in this case, so based on these 3 existing basic the data set we have, so we look at basically the result. So first of all, we can notice that, for instance, for the data set A, if you look at the data set A with the 80%, you can notice that the CNN, it has a better result compared to GCN. It means, so the pink color is better than the green color. This is acceptable because for the data set A, we have a high proportion. And if you want to see that under which conditions, so CNN, it has a low performance, you can please look at the data set C. You can see that the pink color is even, the CNN is lower than GCN. Why? Because CNN, it needs the high number of samples per class. Otherwise, if you don't have this data set, your accuracy is much less. Okay, so based on this result, if you look at what we propose, so what we propose in terms of the accuracy, so it's better than the other cases even compared to the DBN. What is a DBN? It's a deep belief networks, and also in terms of CNN, graph convolution networks, and even the mix of GC and MRF. In total, we notice that if we come from A to C, so based on this condition we have, still we can get an improvement in the diagnostics. So this is basically one of the results has been produced. But of course, there are some other discussion part of this topic, but unfortunately no time I could go more details. But if you are interested, you are welcome to contact me, or we can discuss maybe in the out of the meeting rooms. So based on this result, today we try to give the idea about the weighting between the GCN and CNN and how to combine to get some improvement in the convergence of the basic the loss function, and also to get the improvement in the diagnostics for the different range of the proportion. And this is a limitation in the mechanical application, and more or less we don't have enough data basically to train the model. And this was the one brief conclusion from this presentation. And thank you very much for listening, and if there are any questions, feel free to ask me. Thank you.
Yes, thank you very much for the nice talk. Is there some questions? So maybe I have a simple question. So when you train your network, what are the, so finally you have some trained network, no? And then you use the online data to try to find out if there is some fault or which kind of fault it is. And also which input signals you need. So what are the inputs? What's the physical meaning of the inputs to your neural network?
The data we are using is, okay, thank you. Actually, the data at the beginning I mentioned that we are using the acceleration data because, for example, for this particular machine, so these are the data set we are using. These are the acceleration. So
only is acceleration.
Acceleration. Right.
So only one signal.
It depends. If you have more sensors, of course, you can have more ability to mix.
But you have one machine, so you measure the acceleration once, or speed.
For this machine, depends if acceleration is located for the X or Y or Z. It means we are looking at acceleration in one direction, and that's it. For example, in this milling machine, so we have an acceleration data. So then you can see that we have the motor, the loading, the rotor, and also basically the data acquisition system. Usually we are measuring acceleration data.
So only one input signal.
One input is enough, yes, okay.
Okay. So in the title, so you are handling the time varying speed, right?
Yes,
and so how is the time varying speed taken into consideration? Or it is because, so when you connect your training data, so you have used just change the speeds and...
Okay. Yes, it's a very important question. So but if you want to see what does in the time varying means that you are training your data for one condition and you are testing for another condition. It means A to B, B to C, C to D. It means that you have a data set for condition A, and then you need to train the model. When you train it, then you need to test it, and then you need to verify, validate it, and you are using another data. And that's it. The data set is totally changed, and this is the reason that many algorithms is work for a static one. It means that they are using one condition, but in mechanics, we don't have a static condition, and that's it. We are always changing the data set, and this is the main motivation for this work.
So you mean that when you connect, so thank you. So when you connect the data at one speed, and later in the two working conditions where you use your diagnosis system, you may have some other speed.
Exactly. So we are first collecting data for one speed, and then we are testing for another condition, for another speed.
But during the test or during the connection, the speed is not changed.
But in the mechanics system, you know that if you look at RPM of rotation, of course the machine, it works for one speed for some case, and then suddenly because of loading, because here we have the loading part. So in mechanics, the loading, it changes basically in the continuous is not very sharp. It means it takes some time, the speed change to another speed, but this data is enough for us. And that's it, we don't have too much data, so that's it, always we are lack of enough data. So because I give you one example, if you get for one sampling time 5,000 samples, and these 5,000 samples, you need to take 1024 as a one sample. And these 1024, you have less than 50 samples, and 50 samples is not enough to train the CNN, and that's it. Most of the people work in the fault diagnosis for mechanics, they have a limitation of data, and that's it. Data is very expensive for this area, and there are some open source, but this is not open source, and that's it. It's not easy to access to a lot of data because many companies, they don't provide. But this is the reason that the data is quite limited in this case.
So if you train your network, so you use the current speed and the past speed, you use a piece of time series data, or you use only the current speed?
I think we are fixing a speed and then we collect the data for the acceleration for some time.
Okay.
For example, I mentioned that we are collecting 5,000 samples, for example, and then if you want to use it for the training, you have only 50 samples, and these 50 samples might be for the one class or two class, and then you can imagine that I can tell you that the CNN has a two limitation. First, the input should be image, is a two-dimension. The second, it needs a lot of samples per class, and based on these two limitations, so CNN always is not useful for our application mechanics, and this is the reason that most of the research come to improve this algorithm. And today, what we propose, the GCN and CNN can be combined to overcome the limitation of this proportion of the samples. And this was the very short introduction.
Thank you very much. So is there some other question, please?
One question. So the bearing is not working separately. It's typically working in assembly in the machine and in environment. How you separate the accelerations that are generated by the environment from this acceleration you measured in bearings?
So it means that your question is that how to separate the acceleration from the machine, the sensor connected to the body frame of the machine, or from the noise from environment, right? Okay, so this is the big challenge we have about how much we can trust to the model. Now we have a topic about the trustworthiness model. So today I didn't discuss about the trust because most of this data we are collecting contain the noise, but today I didn't discuss about the effect of the noise. But the noise should be discussed about the resilience of the learning model, and on the top of that, we need to illustrate about some sort of the post-hoc visualization and to show that your result, how much depends on the noise. And that's it. But some of my students, they work on the trustworthiness of the learning model, and we are visualizing the result, how much depends on the noise. And this is if we don't prove it, we don't believe that this result is acceptable. And that's it. The next, if you want to complete this research, we need to come to your question to add the trustworthiness, but otherwise today we don't have time, but we have done some work in this area. Thank you. Thank you.
Okay, so thank you very much. Because of the time, we switch to the next talk. So let's thank the speaker again. So the next presentation will be given by Shinya Churuta from Mitsubishi Electric Company. So, the stage is yours.
Hello everyone, thanks for coming to my presentation. Let me briefly introduce myself. So I'm Shinya Tsuruta. I'm currently working as a visiting researcher at the Mitsubishi Electric Research Laboratory. For last several years, I've developed a predictive maintenance system for factory automations. So today, I would like to introduce a method to remove the noise from the current signal of the induction motors. And the title of my research is Harmonic Signature Extraction in the Motor Fault Detection by a weighted sparsity driven and graph-based model. This is the outline my presentation. The first, I explain the motivation and the background of my research. And the next, I will review the existing methodology related to my work. And then I introduce a proposed method in details. And the next, I will present experiment and discuss of the results. And finally, I will wrap up the conclusion and discuss the future work. Let's start with motivation. Motivation is signal denoising and extracting the signal from the noisy data. And especially, I focus on the eccentricity signal in this presentation. So there are many types of causes of the fault of the induction motor. And the eccentricity is one of the causes. And the induction motor is roughly composed of the rotor and the stator, and so that their centers are aligned. However, their centers may not coincide due to the dimensional variation or the faulty assembly. The eccentricity causes the wear between the rotor and the stator, and it can damage the motor itself. And eccentricity is known to the effect of soft harmonics. The soft harmonics are generated when the rotor bar crosses through the magnetic field between the rotor and the stator. And it is generally known that a sort of harmonics is derived from the description on the slide. So observing the sort of harmonics is so critical to detect the eccentricity. And therefore, the objective of my research is extracting the sort of harmonics of the induction motor. However, the sort of harmonics is so small that they are difficult to detect because they are varying in noise. And generally, sort of harmonics is frequency of the sort of harmonics is 10 times of the driving frequency. Its magnitude is 1/10. And the figure on the right shows the example of the frequency spectrum of the induction motors. And the whose driving frequency is 50 Hz. The sort of harmonics appears more than 500 Hz, and its magnitude is smaller than the noise in the low frequency range. That means the sort of harmonics can be removed by conventional filter techniques, such as high-pass filters. So next, I will review the existing methodology related to my work. This graph-based fault signature extraction method is one of the state-of-the-art denoising technology. And the figure on the left shows the current signal of the induction motor at rotating varying loads. In this method, this current signal is divided by the given window size and the steps. And each window signal is considered a node of the graph structure. And the relationship between each windows are calculated by the cosine similarity. The adjacent windows are considered to contain the almost same signal components, and their cosine similarity is close to the 1. And on the other hand, no adjacent windows are considered to the unrelated. So their similarity is close to the 0. And furthermore, yes, assuming the noise the signal is a dispersed matrix, so it can be calculated by the L1 regularizations. So by auditing the neighboring similarity, I explained the previous slide. So the denoise signal is calculated on this equation on the slide. These three figures shows the results of the signal denoising using the graph-based method. So yellow line is a driving frequency, and the light blue line below it is side band of the driving frequency, indicating the fault. So graph-based method can remove the noise and extract these characteristic signals and compare it to the conventional method. Next, look at the figure below. This is the result of the signal denoising by this graph-based method. And even in this method, the third harmonics are smaller than the noise in the low frequency range. So namely, this method is very useful to extract the characteristic signals around the driving frequency range. And however, this method has difficulty extracting the throat harmonics. To solve these challenges, I propose to add the weight vector to the L1 regularization in this method. Conventional L1 regularizations applies the uniform denoising effect to the all frequency range. So by adding the weight vector, I aim to denoise the measured data to according to the noise level. So weight vector is derived from the physical knowledge. Induction motor is considered as a kind of transformer. The equivalent circuit is shown in the diagram above the right. And the induction motor is equivalent to induction motor with a primary with a stator, and the secondary is a rotor. And the impedance of the stator can be expressed by the resistance and the inductance is shown below. And the current of the stator can be expressed above. It is proportional to the admittance. So the admittance is monotonically decreasing with the frequency. And similarly, the noise envelope is monotonically decreasing as well. In other words, so the weight vector can apply to the noise reduction effect to the vary with the frequency. To evaluate this method, I used this data set of the induction motor. So this data set is measured by our companies and controlled by the varying laws. And this data set, the two types of data. So the first one is the healthy rotor, and the second one is the broken rotor. This slide shows the experimental results of the healthy data. This comparison is in enlarged figures from 400 to the 1000 Hz. From left to the right, the STFT and the minimum variance based and the graph model based and the proposed method. So as you can see that these figures, so the proposed method can remove the noise and extract through the harmonics compared to the conventional method. And next, I compared the theoretical formula with the extracted signals. The figure on the right shows the theoretical formula of the harmonics. So comparing to the right and left figures, and the extracted signal is can match the theoretical formula. And next, these results shows the signal denoising and on the broken rotor. And similar to the previous results, from left to the right, so STFT and the minimum variance based and the graph model based and the proposed method. So even in the broken rotor, so proposed method can extract the certain harmonics and can remove the noise and compared to the conventional method. And also I can compare it to the extracted the theoretical formula with extracted signals. So similar to the previous results. So in this case, the extracted signal is also match the theoretical formula. Finally, let's get down to the conclusions. Weighted graph-based fault signature extraction method has been developed, and this method was evaluated using the health data and the broken bar data of the induction motor, and it showed its effectiveness on the certain harmonic extractions. In the future, I will confirm the effectiveness of this technique in the additional experiments for the eccentricity and the detections. This is the end of my presentation. Thank you for your attention.
So thank you very much for the nice talk. Is there some question? Okay, so maybe I have some question on the page 6. Yes, you have mentioned that you consider here existing technology, so that people consider the dissimilarities between the different pieces of the signals. So what is the reason for that? Why it could work?
So this method is point is the current signal is at the varying the speed. So that the conventional method is assume that the speed is constant. So the varying the speed is become more difficult. So so each window is just a very short time. So when we assume the very short time windows, so each window has the same speed. So we can when we look at the adjacent windows, so we can analyze the same speed analysis.
Okay, thank you. So you mean that it's very short windows here it is used. The next question is, so after you have detected the eccentricity, so on the very, I think the second page, you have said that because of the air gap is different, so people want to find it out by looking at the harmonics. So what do people usually do when they have found out that there's some sort of eccentricity problem? Just shut off the machine or wait and then shut off at some later time?
The eccentricity, so the wear between the rotor and the stator, So so when the eccentricity is more bigger, so the induction motor itself is vibrating. So eccentricity causes more damage to the motor itself.
Okay. Yeah. So thank you very much. Is there some other question? Okay. So it doesn't seem to be this case. So let's thank the speaker again. Okay, so the next talk will be online video. So it is also from the Polytechnical University of Maryland from Professor Karimi's group. So let me start the video.
Hello everyone, good afternoon my colleagues and friends. I'm greeting from Shanghai, China. I'm Dr. Yang, and I'm sorry I cannot be with you in person at the IFIC SAFEPROCESS 2024. I am honored to present my work to such a distinguished audience through this video. Today, I will be discussing a blind denoise method for the vibration signals of rotating machinery. This research is firstly discussed the self-supervised learning framework to do the mission about denoising vibration signals of the rotating machinery. And I'm very excited to share my findings and insights with you. In this presentation, I will cover the background, the proposed framework, dataset, experiments, and the conclusion. My goal is to provide you with a comprehensive understanding of my paper and to contribute to the ongoing conversations and advancement in this field. I will introduce the background first. Rotating machinery is integral to numerous industry processes, powering essential operations across various sectors, including manufacturing, energy production, and transportation. The reliability and performance of these machines are paramount, as adding downtime can lead to significant productivity losses and financial impacts. Two of the most critical components of rotating machinery are the bearings and the gears. Bearing faults are particularly significant because they account for approximately 40% of all faults in rotating machinery. Gear faults, similarly, also accounting for a smaller percentage. They are still crucial, representing about 10% of rotating machinery faults. The red figures are wave shapes of different bearing faults, and in the real-world condition, it is inevitable that signals connected during the monitoring process will inherently encompass red noise. The better the quality of the vibration signals of the rotating machinery, the better the fault diagnosis results. Now let me start to introduce the denoise method. The first part is the traditional signal processing based method, like autoregulation filter, signal value decomposition, and wavelet package decomposition. Here I introduce the two popular traditional denoise methods, autoregulation filter and the similar value decomposition. These two formulas are the calculating processing of the autoregulation filter. The autoregulation filter is a type of filter used in signal processing to predict future values of a signal based on a linear combination of past values. When applied to denoise a signal, the AR filter attempts to separate the underlying signal from the noise by modeling the signal as an autoregressive process. The second method is SVD, and this is a calculation formula. This means a complex signal A can be decomposed into three other matrices: U, sigma, and V transpose. U and V transpose are orthogonal matrices, which represent the rotations or reflections of the signal, which can help in understanding the structure of the signal. Sigma is a diagonal matrix, and its diagonal elements are called signal values. which represents the stress of each component in the decomposition. In order to choose the noise reduction by analyzing the signal values, we can determine which components of the data are important and which are less important. We can then perform a low-rank approximation by keeping only the largest signal values and setting the smaller ones to 0. This effectively filters out the noise and reconstructs the data using only the most significant components. Next, I introduce the background of the machine learning-based denoise method. This is a typical supervised denoise framework where we have both the noise data and the clean data. The noise during the training process, the noise data serves as the input, and the clean data as the output. The difference between the reconstructed data and the actual clean data is then calculated, which is used to optimize the parameters of the framework. So in this case, the framework could be used to remove the noise information in the noise data. Now let me introduce the framework just with the noise data. We get the clean data and we add two different red noise in this clean data. The red noise is for the zero mean Gaussian distribution, and the noise data 1 as the input data and the noise data 2 as the output data. This is the loss function in this self-supervised learning framework. And when the loss function expanded, we could see the first term is the loss function between the clean data and the noise data, and the other three terms are equal to 0 because the noise components follow to the zero mean Gaussian distribution. So let me introduce the dataset. The dataset is a gearbox dataset provided by Southeast University. This gearbox dataset was connected from the drivetrain dynamic simulator shown in the red picture. There are many different fault types for bearings and gearbox. In this table, we could see we have 4 different gearbox faults and 4 different bearing faults. So let me show the results. If we use the bearing vibration signals to test the performance of the proposed framework, we could see the proposed framework could remove the noise parts in the vibration signals in the time domain, and we also could see in the frequency domain the proposed framework could keep the key frequency features in the frequency domain. And we also test the performance of the proposed framework with the gearbox vibration signals. And we also could see the proposed framework could remove the noise in the gearbox vibration signals. In order to demonstrate the performance of the proposed framework, we also test the performance with the auto-regression filter and the SVD. From these two pictures, we could see the auto-regression filter could have the same performance of the proposed framework, and the auto-regression filter could also remove the noise part in the vibration signals and also could keep the key frequency features in the frequency domain. And these are the results based from the SVD decomposition. Let me draw the conclusion here. And the first point is this study demonstrated the effectiveness of a new framework in denoising bearing and gearbox vibration signals, even without having a truly clean signal in the training data. And the second point is because this method relies on self-supervised learning framework, it's tough to get the lower error rate of the regression filter and the SVD. The last point is in order to get a good denoise performance, this self-supervised learning approach needs a large number of training data. And that's all. Thank you all for your attention. If you have any questions and if you are interested in some point I presented today, feel free to contact us by email. Hope we have a nice discussion in the future. And that's all. Thank you.
Okay, so still, let's thank the presenters for the video. So I think the presenter is not online, right? It's no people online, right? Yeah. So no author is online, right? To take the questions. Only one person, which is who is not the author. Okay, then so we finish this one and we come to the next talk. So the next talk will be given by Xiaohan Chen from Xi'an Jiaotong Liverpool University, and he will talk about the multi-modal self-supervised learning for cross-domain one-shot bearing fault diagnosis.
How to full screen? I can't read Italian.
So anybody knows Italian?
It's copy.
This one. I don't know which one. You have the PPT file, no?
No. By the text.
Yes. Yeah, anybody knows that?
Control F, yes. Control L. Doesn't work. Doesn't work. Actually, I think it's this part, but it doesn't work. Control L.
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 Not H.
Doesn't work.
Let me try one too.
Okay, thank you very much. Thank you for your kind introduction from Professor Zhang, and thank you for attending the last presentation of SAFEPROCESS 2024. And the title of my presentation is Multimodal Self-Supervised Learning for Cross-Domain One-Shot Bearing Fault Diagnosis. And we are from University of Liverpool in UK and Xi'an Jiaotong Liverpool University in China. And I'm the first author, Xiaohan Chen. Okay, in this presentation, and I will introduce the background of the bearing fault diagnosis and the research challenges in this area. And in the second section, methodology, I will introduce my methods. And next is the experiments and the conclusion. Okay, let's begin the first part, introduction. I think you are all the expert in this area, so I will very quickly introduce the background of fault diagnosis. And the bearing has a wide range of applications in this area, and bearing plays a very important role in modern industries. But due to prolonged exposure to harsh working conditions, bearing is susceptible to faults. If we can't timely find faults, which may result in serious equipment damages or casualties. So that's the background. And intelligent fault diagnosis methods is very popular in recent years, and the intelligent fault diagnosis method can be roughly divided into the following steps. First, we need to use the sensors, collect faulty data from faulty equipment, and the sensors could be vibration sensors, current sensors, and acoustic sensors. Vibration sensors is the most widely used in this area, and next we process the collected data and input into machine learning algorithms such as support vector machine key decision trees or neural networks. And finally, the machine learning algorithms output predictions. So that's a general procedure for intelligent fault analysis. It's pretty easy. And deep learning method is very popular in recent years. And the deep learning method also achieved great success in this area. But the deep learning methods are based on two assumptions. The first assumption is the training data and the test data follow the same distributions. And the second assumption is that we need a lot of labeled data to train the model. So that's the two problems. And the two assumptions are difficult to meet in practical applications. The first reason is that the distribution of the test data collected from different working conditions or different machines can be is different from that of training data. From this figure, we can find that the classifier trained by the training data, it can perform very well. But when we directly use the pre-trained classifier to the target data, the test data is from different working conditions or different machines or different equipments. But there are lots of misclassification. That's the domain shift problem in this area. And the second problem is that it's very time confusing and laborious to label a large amount of data. It doesn't like computer vision or natural language processing. Everybody can label data, but in fault analysis, we require expert knowledge and work experience. So it's very difficult and expensive to label a large amount of labeled data to train the neural network. And so in order to address the limited labeled data problem, future learning is introduced in this area. And in future learning, we use a very simple example to extract what is future learning. And in future learning, the training data is divided to the support set and the query set. The support set and the query set input into the encoder, and it will generate support embeddings and query embeddings. And we measure their similarities between the query samples and support samples embedding. And finally, in this example, we find that these two fingers they are similar with each other. So if we label the three fingers, label 1, label 2, label 3, label 4, so the query samples class is label 4 because they are similar with each other. So this is a very quick, very simple example of what is future learning. Oh, okay. Thank you. Okay, sorry about that. I will remind it. Okay, there's a limitation of also future learning can address the limited labeled data problem in this area, but there are some limitations about future learning. First, we still need the labeled data to train the model. As we mentioned before, we need to require the support samples, they are all labeled. As we mentioned before, the data label is very difficult for diagnosis. And the problem is, if we have a lot of support samples, the performance is also very good. So future learning methods has trouble in some one-shot scenarios in this area. So the objectives of our model is, the first objective of our method is to address the unlabeled source domain data problem, and the second objective is the cross-domain one-shot problem. We use the finger to illustrate the difference between our method and the conventional fault analysis method. As we can see from the finger, the conventional fault analysis method, they use labeled source domain data to train the model, and then we transfer the knowledge from the source domain to the target domain. But in our method, we use unlabeled data to train the model in the source domain and transfer to the target domain. And in the target domain, for each class, it only contains one sample for each class. So it's a one-shot problem in this article. Okay, that is methodology. Self-supervised learning is a very promising method recently, and we can use self-supervised learning to extract features without any human annotations. As we mentioned before, human annotations is very expensive in this area. In self-supervised learning, we design a pre-text task to train the model, and then without any human annotations, and we transfer the pre-trained knowledge to the downstream text, and we use a very limited level of data to fine-tune the pre-trained model. So that's the basic idea of self-supervised learning to address limited level of data problem. And we are not the first to apply self-supervised learning for diagnosis, but the existing method use the predefined pre-text task directly borrowed from computer vision and natural language processing. But there are lots of differences between images and text and for diagnosis signals. So if we directly from the pre-text task from other research areas, this may influence the final results. And next, existing methods usually only use vibration signal to train the model, but single model signals are susceptible to noise and missing data. So in this work, we use multimodal data to train our self-supervised learning framework. And here is the whole structure of our proposed method. And in this model, in this framework, we use a vibration sensor and acoustic sensor to collect vibration signals and acoustic signals. And then we pre-process the collected data and use short-time Fourier transform and transform the time series signal into spectrums and input into vibration encoder and acoustic encoder, and they will generate vibration features and the acoustic features. Because the vibration signal and the acoustic signal, they are collected from the same bearing, the same 40 bearing at the same time. Although they just in different modalities, but they represent the same meaning in the signal. So they should be similar with each other in a common latent space. So if we maximize their similarities in the common space, we can train the model without adding labeled data. So that's the motivation of our method, and to the best of our knowledge, we are the first to use multimodal data and multimodal self-supervised data to train the model in this area. And after we use the pre-trained model, after we use the self-supervised learning to pre-train the model, and we can go to the pre-trained encoder, and then we reuse the pre-trained encoder to the target domain and input target domain samples and query samples into the pre-trained encoder. It will generate the feature embeddings, and we measure the similarities between query sample embedding and the support sample embeddings. The support class with the highest similarity is considered as a query sample prediction. And next is the experiments. And the dataset is provided by iFlatTech company, and the dataset contains 4 working conditions. It's different loads, and in each condition it contains 5 classes: the normal, catch, breakage, inner race pitting, outer race pitting, and ball pitting. And in this table, illustrates the data information. So in the source domain, in the source domain, each class only contains 30 data, and they are all unlabeled. We use the unlabeled data to pre-train the encoder, and in the target domain, we only have 1 sample for each class, and it's labeled. And these are results. As we can see from the table, and the first two methods, they are transfer learning method, and the last 3 methods, they are fusion learning method. As we can see from the table, it should be mentioned that it's not a very fair comparison, because we use unlabeled source domain data to train our model, but the compared methods, they all use labeled data to train the model. So it's not fair for our method, but our method still achieves the best results in 7 out of 9 cases. And we can say from when we transfer the knowledge from working condition 4 to working condition 1, our proposed method achieves 100% accuracy. So our model performed very well in this study. And here are other data distributions of the test data. As we can say, although we don't use any labeled data to train the model, we still get very clear classification boundaries. Finally, the conclusions, and in this work, we proposed a multimodal self-supervised learning method, and we can use unlabeled data to train the model, and then we reuse the model to the target domain and use to address one-shot, cross-domain one-shot classification problem. And thank you for your attention. And that's my email and the homepage. If you have further questions, you can send an email to me. Thank you very much.
Yeah, thank you very much for the nice presentation. Is there some question? Yes, please.
Please. Microphone.
Thank you for your presentation, and I have a question about the data set. Okay. Because, no, it's okay. In the field of fault diagnosis for bearing, there are some data sets use simulated fault. For example, they use EDM to manufacture a fault on the bearing. So in this data set, is the fault simulated or it is generated in real application?
They are injected into the bearing.
So it's simulated, it's
yes.
manufactured?
Yes.
Okay, thank you very much.
You're welcome. Thank you for your comments.
Okay, some other question? Okay, if not, I have several simple questions. Yes. So the pretext task you have mentioned, so how to understand it in the fault diagnosis context?
So because the data thank you. Because the data are unlabeled, so we need to design a pre-text task to train the model in a supervised manner rather than unsupervised. Because the name of this method is self-supervised learning. That means the trained model is supervised. So we need to design a test, design a pre-text text to generate. You can think it's kind of pseudo label, but it's not actually a pseudo label. You can understand it's kind of pseudo label.
Give an example. What could be the task?
Okay. I will give you an example, but in natural language processing, because such as BERT is a very famous natural language processing model, and we can mask a word in a sentence, and when we input the masked sentence into the model, the output is the original sentence. So that's the label. It's like autoencoder.
Thank you. So
thank you.
Maybe one short question. On the page 16, you have mentioned that you have only 30 samples. What does sample means? It's not the time instant, the value at some given time instant. It's just a piece of data, right?
It's a piece of data because the work has been finished for a long while, so I forgot the sampling rate, but it's a very long sequence, more than 3,000 points. Thank you for your comments.
There's some other question? Okay, if not, then let's thank the speaker again, and we finish this session. We thank all the speakers and audience for your attention. So the closing ceremony will be in the main stage at 18:10. So see you later.